In a distant corner of the universe, two dead stars are locked in a dance that will end in the most violent explosion since creation itself. We think of space as peaceful, a vast, silent ocean dotted with gentle, twinkling lights. But what if I told you that right now, somewhere in the cosmos, forces are building toward an event so catastrophically violent that it makes our most powerful nuclear weapons look like birthday candles? An explosion that forges gold from starlight and hurls the building blocks of planets across millions of light years in a single universe-shaking scream. On August 17, 2017, humanity witnessed something that had never been seen before. A kilonova, the collision of two neutron stars that unleashed more energy in seconds than our sun will produce in its entire 10 billion year lifetime. Join me as we unravel the cosmic crime scene of the most violent event since the Big Bang, and discover how the universe's greatest acts of destruction are also its most profound acts of creation. Before we dive into this cosmic catastrophe, I'm curious, where in the world are you watching from right now, and what time is it there? Drop your location and local time in the comments below. It's fascinating to think that no matter when or where you're watching this, somewhere in the universe, this incredible violence is unfolding. At 8:41 a.m. Eastern Time, on August 17, 2017, the most sensitive scientific instruments humanity had ever built began screaming in unison. Deep underground in Louisiana and Washington state, the twin arms of the LIGO gravitational wave detectors registered something extraordinary, ripples in the very fabric of space and time itself, washing over Earth like waves from an unimaginably violent cosmic storm. Just 1.7 seconds later, the Fermi Gamma Ray Space Telescope detected a burst of the most energetic radiation in the universe. Within hours, telescopes across the globe were swiveling toward a single point in the constellation Hydra, 130 million light-years away. What they found defied every expectation. In that distant galaxy, something was glowing with the light of 200 million suns. Not the familiar steady glow of a star, but something urgent and catastrophic, a flash of brilliance that appeared overnight and began changing color before their eyes. Blue light gave way to red, then infrared, like watching a cosmic fire burn through different fuels. Scientists had protocols for supernovae, gamma-ray bursts, and stellar explosions. But this was different. The gravitational wave signature didn't match any black hole collision they'd seen before. The gamma rays were weaker than expected, but lasted longer. And the optical light, that beautiful, terrifying glow, was following a pattern that existed only in theoretical papers, never before witnessed in reality. Dr. Marcel Soares-Santor, who led one of the first teams to identify the source, later described the moment. We knew we were looking at something that had never been seen before. The excitement was electric, but so was the fear that we might be witnessing the birth of something we didn't understand. The object was designated GW170817, GW for gravitational wave, followed by the date of detection. But as data poured in from observatories around the world and in space, it became clear that this bland designation masked one of the most significant astronomical discoveries in human history. This wasn't just another cosmic explosion. The energy signature, the gravitational waves, the changing colors of light, everything pointed to something scientists had theorized about for decades but never seen: the collision of two neutron stars. And if that was true, then humanity had just witnessed the birth of a kilonova, an explosion so violent that it dwarfed every other known cosmic event except the Big Bang itself. The implications hit the scientific community like a shockwave. For decades, astronomers had wondered how the heaviest elements in the universe were created. Where did the gold in our jewelry come from? What forged the platinum in our electronics, the uranium in our power plants? The answer, it seemed, was written in that changing light from 130 million light-years away. But to understand the true magnitude of what happened on that August morning, we need to examine the clues more carefully, because this cosmic crime scene was about to rewrite everything we thought we knew about the universe. Like detectives arriving at a crime scene, astronomers began analyzing every piece of evidence with forensic precision. The gravitational wave signal told the opening chapter of the story. For the final minutes before collision, LIGO and Virgo detected the characteristic chirp of two massive objects spiraling toward each other. But these weren't the black holes that gravitational wave astronomy had become accustomed to finding. The frequency pattern, the way the signal evolved, pointed to something with mass but also structure, something that could be disrupted and torn apart. The gamma-ray burst provided the second clue. When Fermi and other gamma-ray observatories detected that 1.7-second flash, they were seeing the birth cry of one of the universe's most powerful phenomena. But this gamma-ray burst was peculiar, weaker than the usual cosmic monsters, and pointing in a direction that suggested we weren't looking directly down the barrel of the explosion, but catching it from the side. Then came the optical observations, and this is where the story became truly extraordinary. Within 11 hours of the gravitational wave detection, the SWOPE supernova survey spotted a new point of light in galaxy NGC 4993. What made this discovery remarkable wasn't just the speed, though coordinating global telescope networks to search a specific patch of sky in mere hours was an unprecedented feat of international collaboration. But what the light was telling us. The spectrum of this new source was unlike anything in the astronomical catalogue. It wasn't the hydrogen-dominated signature of a typical supernova, nor the helium and carbon signatures of other stellar explosions. Instead, it showed the fingerprints of much heavier elements, lanthanides, rare earth metals, elements that required incredibly neutron-rich environments to form. As telescopes continued monitoring the source over the following weeks, they witnessed something even more remarkable. The light was evolving in real time, changing color from blue to red to near-infrared. This wasn't the relatively stable glow of a star, or even the predictable fade of a typical supernova. This was the signature of freshly forged heavy elements, cooling and expanding into space. Dr. Ryan Foley, whose team was among the first to obtain detailed spectra, explained the significance. We were watching nucleosynthesis happen in real time. We were seeing elements being created and cooling before our eyes. It was like watching the universe's forge at work. The evidence was overwhelming and pointed to a single, extraordinary conclusion. But to fully grasp what humanity had witnessed, we need to understand what could create such incredible violence and why this single event would change our understanding of the cosmos forever. By the end of August 2017, the astronomical community had reached a consensus that would have seemed like science fiction just months earlier. Humanity had witnessed the collision of two neutron stars, creating what scientists call a kilonova, literally meaning 1,000 novae. But to call this simply another type of cosmic explosion would be like calling the Grand Canyon just another hole in the ground. What happened in galaxy NGC 4993 represented a fundamental milestone in our understanding of the universe, comparable to the first detection of gravitational waves or the discovery of the cosmic microwave background radiation. Consider the energy scales we're discussing. In the final seconds before collision, the two neutron stars were orbiting each other at nearly 30% the speed of light. That's roughly 90,000 kilometers per second. The gravitational forces involved were so extreme that they were literally stretching and compressing space-time itself, creating ripples that propagated across 130 million light-years to gently nudge LIGO's laser beams by less than 1/10,000th the width of a proton. When the collision finally occurred, it released more energy in gravitational waves alone than the total light output of every star in the observable universe combined. Let that sink in for a moment. For a brief instant, this single event outshone every star, every galaxy, every quasar in the visible cosmos, not in light, but in the fundamental distortion of space and time. The kilonova explosion that followed was equally staggering. The blast ejected material equivalent to several Earth masses at speeds of up to 30,000 kilometers per second. This expanding cloud of debris, heated to temperatures of billions of degrees, began glowing with the combined luminosity of 200 million suns. For comparison, That's roughly equivalent to the total light output of our entire Milky Way galaxy during its most active star-forming periods. But the true significance of GW 170817 went far beyond its impressive energy budget. This single event solved multiple cosmic mysteries that had puzzled scientists for generations. To understand the incredible violence of a kilonova, we must first meet the cosmic players involved: neutron stars, the most extreme objects in the known universe. Imagine taking the mass of our Sun, that's 330,000 times the mass of Earth, and compressing it into a sphere just 20 kilometers across. The result would be so dense that a single teaspoon of this material would weigh roughly 6 billion tons. That's equivalent to taking Mount Everest and compressing it down to the size of a sugar cube. This isn't science fiction. This is the reality of neutron stars. These cosmic monsters are made almost entirely of neutrons, the particles normally found in atomic nuclei alongside protons. But in a neutron star, the gravitational pressure is so intense that it crushes atoms themselves out of existence. Electrons are forced to merge with protons, creating a solid ball of pure neutron matter held together by gravity, so powerful it warps space-time around it. The physics at play here push the very limits of what matter can endure. The pressure at a neutron star's core exceeds anything we can create in laboratories by factors of trillions. It's denser than the nucleus of an atom, yet exists on a scale large enough to be seen from space. Russian physicist Lev Landau, who first predicted these objects in 1932, called them one giant atomic nucleus held together by its own gravity. But density is only part of what makes neutron stars so extraordinary. Their magnetic fields are the strongest known in the universe, typically 1 trillion times stronger than Earth's magnetic field, and in some cases up to 1,000 times stronger than that. These magnetic fields are so intense, they would instantly kill any living thing within 1,000 kilometers and could erase every credit card on Earth from the distance of the Moon. Then there's their rotation. Many neutron stars spin at incredible rates, some completing a full rotation in just milliseconds. The fastest known neutron star, PSRJ 1748, Rus 2446 AID, spins 716 times per second. At this rate, a point on its equator is moving at roughly 70,000 kilometers per second, nearly 25%. The speed of light, the fact that these objects don't tear themselves apart at such rotational speeds, speaks to the incredible binding force of their gravity. Dr. Anna Watts, a leading neutron star researcher, puts their extremeness in perspective. Neutron stars are natural laboratories for physics we can never recreate on Earth. They represent matter under conditions so extreme that they test the very boundaries of our understanding of how the universe works. The surface of a neutron star is equally alien. Despite temperatures that can reach millions of degrees, the immense gravity creates a surface so smooth that any irregularities would be measured in millimeters. The atmosphere, if you can call it that, is composed of hydrogen just a few centimeters thick, but weighs as much as Earth's entire atmosphere due to the crushing gravity. Perhaps most remarkably, neutron stars exist right at the edge of physical possibility. Add just a little more mass, perhaps 20% more, and the neutron degeneracy pressure that keeps them stable would fail. Gravity would win the ultimate battle, and the neutron star would collapse into a black hole, disappearing from our universe forever. This precarious balance makes binary neutron star systems, two of these monsters orbiting each other, among the most unstable configurations in the cosmos. They represent cosmic time bombs, slowly losing energy through gravitational wave radiation, spiraling ever closer until the inevitable moment when they cross the point of no return. When that moment comes, when two city-sized objects, each containing more mass than our Sun, collide at relativistic speeds, the result is beyond violent. It's a cosmic catastrophe that reshapes our understanding of physics itself. The story of every neutron star begins not with a whimper, but with the most spectacular death in the universe, the collapse of a massive star in a core collapse supernova. Picture a star, at least 8 times more massive than our Sun, burning through its nuclear fuel in the cosmic equivalent of a drag race. While our sun will leisurely burn hydrogen for 10 billion years, these stellar giants consume their fuel at such a furious pace that they live fast and die young, their entire lifespans measured in mere millions of years. The death spiral begins when the star starts producing iron in its core. Iron is the cosmic dead end, the most stable nucleus in the universe. Unlike lighter elements, fusing iron absorbs energy rather than releasing it. When a massive star's core becomes dominated by iron, it's like a fire trying to burn ash. The nuclear furnace that has supported the star against its own crushing gravity suddenly shuts down. What happens next unfolds with terrifying speed. In less than a second, the iron core, initially about the size of Earth, collapses to a sphere just 20 kilometers across. This isn't gradual compression, it's catastrophic freefall. The core's density increases by a factor of 100 trillion in the blink of an eye. The gravitational potential energy released in this collapse is so enormous that it exceeds the total energy output of our sun over its entire 10 billion year lifetime. And it all happens in less time than it takes you to blink. The collapse only stops when the core becomes so dense that the neutrons themselves refuse to be compressed further. This creates what physicists call neutron degeneracy pressure, a quantum mechanical effect that provides the last line of defense against complete gravitational collapse. The infalling matter hits this incredibly dense core and rebounds like a cosmic basketball bouncing off an immovable wall. The rebound launches a shockwave that races outward through the star at 30,000 kilometers per second, sheeting the stellar material to billions of degrees and blasting the star's outer layers into space with the energy of 10 billion suns. This is a core collapse supernova, one of the most energetic events in the universe. Dr. Adam Burrows, who has spent decades modeling these explosions, describes the violence. In 1 second, the core of a massive star transforms from something the size of Earth to something smaller than Manhattan, while simultaneously launching an explosion that can be seen from billions of light years away. It's the most dramatic transformation in nature. But here's what makes this process even more remarkable. Not every massive star that undergoes core collapse produces a neutron star. If the stellar core is too massive, above about 25 solar masses, even neutron degeneracy pressure isn't enough to stop the collapse. In these cases, gravity wins completely, and the core continues collapsing into a black hole, taking the supernova explosion with it and creating what astronomers call a failed supernova. The neutron stars that do form from this process are born spinning rapidly and with intense magnetic fields, inheriting the angular momentum and magnetic flux of their massive stellar progenitors, but concentrated into an object just 20 kilometers across. It's like a figure skater pulling in their arms during a spin, but taken to an almost incomprehensible extreme. These newborn neutron stars are among the most violent objects in the universe. Their surfaces are churning with starquakes that release more energy than the largest earthquakes in Earth's history. Their magnetic fields accelerate particles to near light speed, creating beams of radiation that sweep across space like cosmic lighthouses. Yet for all their individual violence, these stellar corpses can find companions, other neutron stars born from binary star systems, where both massive stars underwent core collapse. And when two neutron stars find themselves locked in gravitational embrace, they begin the final chapter of their story. A slow spiral dance that will end in the most violent collision since the Big Bang itself. In the vast emptiness between stars, two neutron stars begin a dance that will last millions of years and end in cosmic catastrophe. Binary neutron star systems are rare cosmic accidents, the survivors of an extraordinarily unlikely sequence of events. For two neutron stars to end up orbiting each other, you need a binary star system, where both stars are massive enough to undergo core collapse, but not so massive that they form black holes. The stars must also survive the violence of two supernova explosions without being blown apart or ejected from the system. The odds against this happening are astronomical. In our entire Milky Way galaxy, containing over 100 billion stars, a Astronomers estimate there are only about 100,000 binary neutron star systems. That's roughly one for every million stars, making them among the rarest configurations in the cosmos. But when these systems do form, they become cosmic time bombs. The two neutron stars, each typically separated by distances comparable to the radius of our Sun, begin orbiting each other at tremendous speeds. Unlike planets in our solar system, which orbit in stable, unchanging ellipses, neutron star binaries are slowly but inevitably losing energy. The culprit is Einstein's general relativity. According to Einstein's equations, any accelerating mass should create ripples in space-time, gravitational waves. For most objects, this effect is so tiny as to be negligible. Earth, for instance, loses energy to gravitational waves as it orbits the Sun, but at such a slow rate that our planet won't spiral into the Sun for trillions upon trillions of years, long after the Sun itself has died. But neutron stars are different. Their immense mass and compact size create gravitational fields so strong that they generate gravitational waves at a much more significant rate. As these waves carry energy away from the system, the orbital distance shrinks and the neutron stars spiral closer together. The beautiful tragic irony is that as the stars lose energy, they actually speed up, like ice skaters pulling their arms closer to their bodies. The neutron stars orbit faster and faster as they draw nearer. This creates a feedback loop. Faster orbits generate stronger gravitational waves, which carry away more energy, causing the stars to spiral inward even more rapidly. For most of the system's lifetime, perhaps millions or even billions of years, this process is incredibly gradual. The neutron stars might lose only millimeters per year in their separation distance, but as they get closer, the process accelerates exponentially. In the final years, they lose meters per year. In the final days, kilometers per day. In the final hours, the orbital decay becomes measurable in real time. The Hulse-Taylor pulsar system, discovered in 1974, provided the first indirect evidence of gravitational waves by showing exactly this behavior. Astronomers Russell Hulse and Joseph Taylor measured the orbital decay of this binary pulsar with such precision that they could confirm Einstein's predictions within a fraction of a percent, work that earned them the Nobel Prize in Physics. But PSR B1913+16, the Hulse-Taylor pulsar, won't merge for another 300 million years. Other systems are much closer to their cosmic appointment with destiny. As the neutron stars approach their final moments, the gravitational forces between them become so intense that they begin to distort each other's shapes. These perfectly spherical objects start to bulge and stretch, raising massive tides on their surfaces. The stars become tidally locked, always showing the same face to each other, like a cosmic pas de deux frozen in perpetual embrace. The gravitational waves they emit in these final stages become strong enough to be detected by instruments like LIGO, if we're lucky enough to be listening when they merge. And when that moment finally comes, when two neutron stars traveling at 30% the speed of light finally touch after millions of years of cosmic choreography, the result is beyond violent. It's the birth of a kilonova and the most spectacular finale in the universe. The final act of a binary neutron star system unfolds across millions of years, but the last few minutes contain more drama than the entire previous lifetime of both stars combined. For eons, the two neutron stars have been locked in their gravitational embrace, spiraling inward so slowly that the change would be imperceptible to human observation. But physics is patient, and Einstein's equations are inexorable. As gravitational waves carry away the system's orbital energy, the dance of destruction accelerates with mathematical precision. The process follows what physicists call an in-spiral, a spiral trajectory that tightens exponentially as the neutron stars lose energy. For most of the system's history, this energy loss occurs at a leisurely pace. The neutron stars might approach each other by mere centimeters per year, a rate so slow that it would take sensitive radio telescopes decades of observation to measure. But as the separation decreases, the gravitational wave emission increases dramatically. The power radiated in gravitational waves scales with the inverse fifth power of the orbital separation, meaning that as the neutron stars get twice as close, they radiate 32 times more energy. This creates a runaway effect that transforms millions of years of gradual approach into a final crescendo of violent acceleration. Dr. Kip Thorne, the theoretical physicist who won the Nobel Prize for his work on gravitational waves, describes this process as one of nature's most perfect examples of positive feedback. The closer the neutron stars get, the faster they spiral inward, and the faster they spiral, the more energy they radiate, causing them to spiral even faster still. In the final year before merger, the neutron stars are close enough that their mutual gravitational influence begins to affect their internal structure. These objects, which have maintained their perfectly spherical shapes for millions of years, start to deform under each other's tidal forces. The neutron star surfaces begin to bulge outward in the direction of their companion, creating tidal bulges similar to Earth's ocean tides, but made of neutron matter billions of times denser than water. As the months count down to collision, the orbital period drops from hours to minutes. The neutron stars, each just 20 kilometers across, are now orbiting their common center of mass hundreds of times per second. At these speeds, the stars themselves begin to experience significant relativistic effects, time dilation, length contraction, and frame dragging effects that would make Einstein's head spin. The gravitational waves being emitted during this phase carry power equivalent to the light output of all the stars in the observable universe combined. Yet this energy is carried not by electromagnetic radiation, but by ripples in space-time itself, distortions so subtle that they require the most sensitive instruments humanity has ever built to detect them across cosmic distances. In the final weeks, something remarkable happens. The neutron stars become tidally locked, always showing the same face to each other, like a cosmic binary dance. Their rotation periods synchronize with their orbital period, creating a system where both stars spin and orbit in perfect harmony. It's a brief moment of cosmic choreography before the final catastrophe. The tidal forces during this phase are beyond imagination. Each neutron star raises tides on its companion that are kilometers high, tides made not of water, but of neutron matter, so dense that a thimbleful would weigh as much as a mountain. These tidal bulges create additional sources of energy, dissipation, accelerating the inspiral even further. Radio astronomers fortunate enough to observe a binary neutron star system during its final years witness something extraordinary: the gradual speed-up of the pulsar signals as the orbital period decreases. It's like listening to a cosmic metronome that slowly but inexorably increases its tempo, building toward a crescendo that will end in silence. In the final days, the gravitational wave frequency sweeps upward through the range that LIGO and Virgo can detect. If the system is close enough and oriented favorably, ground-based gravitational wave detectors begin picking up the signal, first as a barely detectable whisper, then growing stronger as the frequency increases and the amplitude grows. The neutron stars are now so close that they're orbiting each other inside. Oh, what have been the diameter of a typical white dwarf star? Their surfaces are just hundreds of kilometers apart, and the gravitational forces between them are approaching the binding energy that holds each neutron star together. At this point, there's no turning back. The system has crossed the threshold where gravitational wave emission dominates all other effects. The neutron stars are committed to their collision course, and nothing in the known universe can prevent what's about to happen. The final hours have begun, and with them, the countdown to the most violent event the cosmos has witnessed since the Big Bang itself. In the last 60 seconds before collision, physics enters a realm where theory meets the absolute limits of nature's violence. The two neutron stars are now orbiting each other at a significant fraction of the speed of light, roughly 60,000 kilometers per second at their surfaces. To put this in perspective, they're moving so fast that they could circle Earth's equator in less than a second. Yet they're still bound by gravity, locked in a death spiral that's about to reach its ultimate conclusion. The gravitational waves being emitted during these final moments are so powerful that they carry away the equivalent of several solar masses in pure energy every second. This isn't matter being converted to energy. This is space-time itself being distorted so violently that it radiates away the gravitational binding energy that has held these objects together for millions of years. LIGO and Virgo detectors, if they're listening, record a signal that sweeps from about 30 Hz to over 1000 Hz in these final seconds, a cosmic chirp that rises in both frequency and amplitude, like the universe's most dramatic crescendo. The strain on the detector arms increases exponentially, reaching peak amplitudes that stretch and compress the 4-kilometer laser interferometers by distances comparable to 1/10,000th the width of a proton. But the real drama is happening 130 million light-years away, where two city-sized objects containing more mass than our Sun are about to experience the most violent collision in the known universe. At 10 seconds before contact, the neutron stars are orbiting each other 100 times per second. Their surfaces are now just 200 kilometers apart, a distance less than that between New York and Philadelphia. The tidal forces are so intense that both neutron stars begin to visibly deform, stretching toward each other like cosmic teardrops. The neutron matter that has remained stable for millions of years under the crushing force of gravity now begins to flow and reshape under tidal stresses. At 1 second before contact, the orbital frequency reaches 300 Hz. The neutron stars are so close that their outer layers are beginning to interact gravitationally. Material from the outer crusts, the least tightly bound matter on each neutron star, begins to stream between the two objects, forming bridges of neutron-rich plasma heated to billions of degrees. At 0.1 seconds before contact, something extraordinary happens. The neutron star's magnetic fields, each trillions of times stronger than Earth's, begin to interact and reconnect. This creates the first electromagnetic signature of the impending collision, a brief precursor of high-energy radiation that races outward at the speed of light, arriving at Earth 1.7 seconds before the gravitational wave signal from the actual collision. The final 0.01 seconds are where human intuition completely breaks down. The neutron stars are now so close that their event horizons, the theoretical boundaries within which nothing can escape their combined gravitational pull, begin to overlap. General relativity predicts that space-time around the merger becomes so curved that light rays bend into spirals, and the usual concepts of space and time lose their meaning. Dr. Masaru Shibata, whose computer simulations have mapped these final moments in unprecedented detail, describes the challenge. We're trying to solve Einstein's equations in a regime where space-time itself is oscillating wildly, where matter is compressed beyond nuclear density, and where the speeds involved approach the ultimate cosmic speed limit. It pushes our computational methods to their absolute limits. The neutron star's surfaces finally touch, but this isn't a gentle contact. It's a collision at 30%. The speed of light between objects whose surfaces are harder than atomic nuclei. The kinetic energy involved in this collision exceeds the rest mass energy of our entire solar system. In the final milliseconds, the neutron stars don't so much collide as interpenetrate. Their outer layers are torn away by tidal forces and flung into space at tremendous velocities, while their cores merge into a single incredibly dense object. The collision creates a shockwave that propagates through both neutron stars at near light speed, disrupting the neutron degeneracy pressure that has kept them stable and triggering a cascade of nuclear reactions. The merger itself lasts just a few milliseconds, but in that brief time, several remarkable things happen simultaneously. First, the collision creates the strongest gravitational waves ever produced since the Big Bang, ripples in space-time, so powerful that they carry the signature of this violence across the entire observable universe. Second, the disruption of ultra-dense neutron matter creates conditions not seen anywhere else in the modern universe. Neutrons that have been locked in stable configurations for millions of years are suddenly free to undergo rapid nuclear reactions, creating atomic nuclei far heavier than anything that exists in nature on Earth. Third, the collision triggers the formation of a massive accretion disk around the newly merged object, a swirling maelstrom of neutron-rich matter heated to temperatures exceeding 10 billion degrees. This disk contains several Earth masses of the heaviest elements in the universe, all compressed into a region smaller than our solar system. The gravitational wave signal that LIGO detects ends abruptly when the neutron stars merge. But this isn't the end of the story. It's just the beginning. The collision has created conditions so extreme that they're about to trigger the most violent explosion in the cosmos, a kilonova. What emerges from this cosmic catastrophe will reshape our understanding of how the universe creates its heaviest elements and reveal that the most violent events in nature are also the most creative. The collision itself unfolds in a chaos of physics, so extreme that it challenges the very foundations of our understanding of matter, energy, and space-time. When two neutron stars finally touch after their million-year death spiral, the result isn't a simple crash. It's a catastrophic interpenetration of matter compressed to the edge of physical possibility. The collision occurs at velocities approaching 100,000 kilometers per second, with kinetic energies that dwarf anything else in the known universe except the Big Bang itself. The first thing that happens is the complete disruption of both neutron stars' outer layers. These objects, which have maintained perfect spherical shapes under their own crushing gravity for millions of years, are literally torn apart by tidal forces in milliseconds. The outermost regions of each neutron star, layers of neutron-rich matter that would weigh billions of tons per cubic centimeter, are stripped away and flung into space like cosmic shrapnel. But this is just the opening act. The cores of the neutron stars, containing the vast majority of their mass, merge in a process that creates the most extreme physical conditions in the modern universe. For a brief moment, the collision creates matter densities that exceed those found in atomic nuclei, regions where neutrons are packed so tightly that normal physics breaks down and exotic forms of matter may briefly exist. Dr. Luciano Rezzola, whose supercomputer simulations have revealed the intricate details of these mergers, explains the violence. In the span of a few milliseconds, we go from two separate neutron stars to a single, incredibly hot, rapidly rotating object that's teetering on the edge of collapse into a black hole. The physics involved pushes every known theory to its breaking point. The merger creates what physicists call a hypermassive neutron star, an object that contains more mass than any stable neutron star should be able to support, held up only by its rapid rotation and the thermal pressure from the incredible heat generated by the collision. This object spins hundreds of times per second, so fast that material at its equator is moving at nearly 20% the speed of light. The hypermassive neutron star is surrounded by a massive accretion disk, a swirling disk of neutron-rich matter that contains several Earth masses of material heated to temperatures exceeding 10 billion degrees Kelvin. This disk extends for hundreds of kilometers around the central object and represents one of the most extreme environments in the known universe. Within this disk, conditions are perfect for the rapid neutron capture process, the R process, that creates the heaviest elements in the periodic table. Free neutrons, liberated from the disrupted neutron star matter, are captured by lighter atomic nuclei at rates millions of times faster than anything possible in terrestrial laboratories or even in the cores of the most massive stars. The electromagnetic signature of the merger begins almost immediately. The collision of the neutron star's ultra-strong magnetic fields creates a brief but intense burst of gamma rays, photons so energetic that a single gamma ray carries more energy than all the visible light our sun produces in a second. This gamma ray burst races outward at the speed of light, creating a beacon that can be detected across cosmic distances. But the most spectacular part of the show is yet to come. The hypermassive neutron star created by the merger is fundamentally unstable. Within seconds or minutes, it faces an inevitable fate. Either it will shed enough mass and angular momentum to become a stable neutron star, or it will collapse under its own gravity to form a black hole. Current models suggest that for mergers involving the typical masses observed by LIGO, collapse to a black hole is the most likely outcome. When this collapse occurs, it triggers the ejection of the accretion disk at tremendous velocities. Material that was heated to billions of degrees and enriched with freshly synthesized heavy elements is blasted into space at speeds of up to 30,000 kilometers per second, roughly 10% the speed of light. This expanding cloud of debris, containing gold, platinum, uranium, and dozens of other heavy elements, begins to glow with the combined luminosity of hundreds of millions of suns. The heat comes not from fusion or fission, but from the radioactive decay of unstable isotopes created during the R process, elements so neutron-rich that they don't exist naturally anywhere on Earth. The expanding debris cloud creates what astronomers call a kilonova, an explosion 1,000 times brighter than a regular nova, and the most violent event in the universe since the Big Bang. But unlike a supernova, which destroys heavy elements as often as it creates them, a kilonova is a pure creator, a cosmic forge that transforms the neutron matter from dead stars into the building blocks of future planets and life. The collision that began as a simple merger of two neutron stars has now become something far more profound. The universe's primary factory for creating the heaviest elements and a cosmic recycling center that transforms stellar death into the seeds of future creation. The real fireworks are just beginning. In the final moments of the neutron-star merger, space-time itself becomes a medium for violence, carrying the signature of cosmic catastrophe across the entire observable universe. The gravitational waves produced by the collision represent something fundamentally different from any other form of radiation we know. Unlike light, radio waves, or gamma rays, all forms of electromagnetic radiation that can be absorbed, scattered, or blocked, gravitational waves are distortions in the fabric of space-time itself. They pass through planets, stars, and entire galaxies as if they weren't there, carrying an unfiltered message about the violence that created them. When LIGO detected GW 170817 on August 17, 2017, the instruments measured space-time distortions that had traveled 130 million years to reach Earth. Think about that for a moment. The ripples in space-time that gently nudged LIGO's laser beams began their journey when complex life was just beginning to flourish on Earth, carrying information about a cosmic catastrophe that occurred when our planet looked nothing like it does today. The technical achievement of detecting these waves borders on the miraculous. The gravitational wave signal from GW 170817 stretched and compressed LIGO's 4-kilometer arms by a distance smaller than 1/10,000th, the width of a proton. To put this in perspective, if you could somehow expand a proton to the size of a marble, the space-time distortion LIGO measured would be equivalent to changing the distance between Earth and the nearest star by the width of a human hair. Dr. Kip Thorne, whose theoretical work laid the foundation for gravitational wave astronomy, describes the significance. For the first time in human history, we're not just seeing the universe, we're feeling it. Gravitational waves let us sense the universe through a completely different sense, like suddenly gaining the ability to hear after a lifetime of being deaf. The gravitational wave signal from GW 170817 told a story that unfolded in real time. For the first 100 seconds of the detection, LIGO and Virgo recorded the characteristic chirp of two neutron stars spiraling toward each other, a signal that swept from 30 Hz to over 1,000 Hz. As the orbital frequency increased exponentially, the amplitude grew steadily as the neutron stars approached, reaching peak intensity just milliseconds before the merger. Then, abruptly, the signal disappeared. This sudden cutoff marked the moment when the two neutron stars finally touched and merged, ending their million-year spiral dance in a collision so violent that it briefly outshone the combined gravitational wave emission of every other source in the universe. The merger itself was too complex and chaotic for current gravitational wave detectors to resolve. The signal disappeared into a noise floor that represents the current limits of human technology. But what LIGO and Virgo captured was more than just another gravitational wave detection. The signal provided direct confirmation of theoretical predictions that had been debated for decades. The way the frequency increased, the rate at which the amplitude grew, the precise timing of the final merger, all matched computer simulations of neutron star collisions with remarkable accuracy. Perhaps most importantly, the gravitational waves arrived at Earth just 1.7 seconds before the gamma-ray burst detected by the Fermi telescope. This tiny time difference confirmed one of Einstein's most fundamental predictions, that gravitational waves travel at exactly the speed of light. After more than a century, we had direct experimental proof that space-time distortions and electromagnetic radiation propagate at the same cosmic speed limit. The gravitational wave detection also provided crucial information about the neutron stars themselves, all by analyzing the signal's evolution. Scientists could determine that the two neutron stars had masses of approximately 1.17 and 1.60 times the mass of our Sun, typical values for neutron stars, but the first time such measurements had been made using gravitational waves rather than electromagnetic observations. The Sophia Sov is per Sov isip. But the gravitational waves were just the opening notes of a cosmic symphony that was about to crescendo into the most violent electromagnetic display in the universe. Just as the space-time ripples began their journey toward Earth, the merger was triggering events that would create one of the most powerful gamma-ray bursts ever observed and set the stage for an explosion that would outshine entire galaxies. Just 1.7 seconds after LIGO detected the final gravitational wave chirp from GW 170817, the Fermi Gamma-Ray Space Telescope recorded something that made astronomers around the world sit up and take notice. A short gamma-ray burst unlike anything they had ever seen before. Gamma-ray bursts are among the most violent phenomena in the known universe. These brief flashes of the most energetic form of electromagnetic radiation can release more energy in seconds than our Sun will produce in its entire 10 billion year lifetime. They're so powerful that a gamma-ray burst occurring in our own galaxy could potentially sterilize Earth from a distance of thousands of light-years. The gamma-ray burst from GW 170817, designated GRB 170817A, was different from the typical cosmic monsters that astronomers had grown accustomed to studying. Most gamma-ray bursts are so bright that they can be detected from billions of light-years away across the entire observable universe. But GRB 170817A was what astronomers call underluminous, about 1,000 times fainter than a typical short gamma-ray burst. At first, this seemed puzzling. If the neutron star merger was as violent as the gravitational wave suggested, why was the gamma-ray burst so relatively weak? The answer lay in understanding the geometry of the explosion and our cosmic vantage point. Dr. Eleonora Troja, whose team led some of the early gamma-ray observations, explains the breakthrough. We realized we weren't looking directly down the barrel of the gamma-ray burst jet, but rather seeing it from the side. It's like the difference between looking directly into a flashlight beam versus seeing it from an angle. The energy was there, but it was beamed away from us. This geometric insight was crucial because it solved a decades-old mystery about the connection between neutron star mergers and gamma-ray bursts. Theoretical models had long predicted that colliding neutron stars should produce short gamma-ray bursts, but the evidence had remained circumstantial. GRB 170817 provided the smoking gun, direct proof that neutron star mergers are indeed the engines behind at least some of the universe's most violent electromagnetic explosions. The mechanism behind this gamma-ray production is a masterpiece of extreme physics. When the two neutron stars merge, they create a highly magnetized, rapidly rotating object surrounded by an accretion disk of neutron-rich matter. The combination of strong magnetic fields and rapid rotation acts like a cosmic particle accelerator, creating jets of plasma moving at nearly the speed of light. These relativistic jets punch through the expanding debris from the merger, creating shockwaves that accelerate electrons to tremendous energies. When these ultra-high energy electrons spiral around magnetic field lines, they emit synchrotron radiation in the gamma-ray portion of the electromagnetic spectrum. Photons so energetic that each one carries millions of times more energy than visible light. The jets themselves are remarkably narrow, typically just a few degrees wide, like cosmic laser beams of destruction. This explains why GRB 170817A appeared so much fainter than typical gamma-ray bursts. We were seeing the edge of the jet rather than looking directly into it. Computer simulations suggest that if we had been positioned directly in the path of the jet, GRB 170817A would have appeared as bright as the most powerful gamma-ray bursts ever detected. But the gamma-ray burst was just the beginning of the electromagnetic fireworks. As the relativistic jets plowed through the expanding kilonova debris, they created additional shockwaves that would continue to brighten and evolve over the following months. This afterglow emission provided astronomers with a way to study the merger's aftermath in unprecedented detail. The discovery that neutron star mergers produce gamma-ray bursts had profound implications for our understanding of these cosmic explosions. It meant that every short gamma-ray burst detected by satellites like Fermi and Swift might represent a kilonova explosion occurring somewhere in the universe, a cosmic forge creating heavy elements and scattering them into space. The energy scales involved in producing these gamma-ray bursts are almost incomprehensible. The relativistic jets carry energy equivalent to the rest mass of several Earths, all focused into beams just a few degrees wide. When these jets interact with the surrounding medium, they can remain detectable for months or even years after the initial explosion. Dr. Wenfei Fong, who has spent years studying short gamma-ray bursts, puts the significance in perspective. GRB 170817A taught us that we've been seeing the signatures of kilonova explosions for decades without realizing it. Every short gamma-ray burst we detect might represent a cosmic factory creating gold, platinum, and other heavy elements somewhere in the universe. The gamma-ray burst from GW 170817 also provided crucial information about the merger's immediate aftermath. The fact that gamma rays were produced at all told astronomers that at least some material had been ejected from the merger at ultra-high velocities, material that would soon begin glowing in optical light as it expanded and cooled. This was the birth cry of a kilonova, and the most spectacular part of the show was yet to come. 11 hours after the gravitational wave detection, telescopes around the world turned toward a small patch of sky in the constellation Hydra and witnessed something that would rewrite our understanding of cosmic violence: the birth of a kilonova. The Swope Supernova Survey Telescope in Chile was the first to spot it, a new point of light in galaxy NGC 4993 that hadn't been there the day before. Within hours, dozens of ground-based and space-based telescopes were trained on this single source, creating the most comprehensive observation campaign in astronomical history. What they saw was unlike anything in the cosmic catalogue. The kilonova began as a brilliant blue-white light, initially outshining the entire galaxy that hosted it. But this wasn't the steady glow of a star, or even the relatively predictable evolution of a supernova. This was something dynamic and chaotic, a light source that was visibly changing color and brightness in real time as astronomers watched. The term kilonova literally means 1,000 novae, and the name understates the violence involved. At its peak, the explosion from GW 170817 was producing light equivalent to 200 million suns, imagery, making it temporarily one of the brightest objects in the local universe. To put this in perspective, the kilonova was brighter than all the stars in the Milky Way combined during our galaxy's most active star-forming periods. Ispam Savrovia Drovi 17 Sivarovi A is But raw luminosity was just part of what made this explosion so extraordinary. The real revelation came from spectroscopic analysis, breaking down the kilonova's light into its component wavelengths to read the cosmic fingerprints of the elements being created in real time. Dr. Ryan Foley, whose team obtained some of the first detailed spectra, describes the moment of discovery. We were seeing the signatures of elements that had been created just hours before our observations. We were literally watching nucleosynthesis happen, the universe forging gold and platinum and sending them streaming into space. Dr. Ryan Foley, whose team obtained some of the first detailed spectra, describes the moment of discovery. The physics behind kilonova emission is a story of cosmic alchemy on the grandest scale. The expanding debris cloud from the neutron star merger contains several Earth masses of freshly synthesized heavy elements. Elements so neutron-rich that most don't exist naturally anywhere on Earth. These unstable isotopes undergo radioactive decay, releasing energy that heats the expanding material and causes it to glow. Unlike a supernova, which gets its energy primarily from the initial explosion, a kilonova is powered by the ongoing decay of radioactive elements. It's like a cosmic nuclear reactor, but instead of controlled fusion, it's fueled by the decay of elements that were created in the most extreme conditions in the universe just hours or days earlier. The color evolution of the kilonova told a fascinating story about the elements being created. In the first few days, the expanding debris was dominated by lighter elements, iron, nickel, and cobalt, which glowed with blue and ultraviolet light. But as the debris expanded and cooled, heavier elements began to dominate the emission. Within a week, the kilonova had shifted from blue to red, then to near-infrared light. This color change revealed the presence of lanthanides, rare earth elements that are extraordinarily difficult to create, and had never before been directly observed forming in space. The specific wavelengths of light being absorbed and emitted provided a cosmic barcode that identified elements like europium, gadolinium, and terbium. Dr. Durrach Watson, whose team identified these heavy elements in the kilonova spectrum, explains the significance we were seeing the cosmic production line for the rarest elements in the universe. These are elements that make up less than 1 part per billion of typical cosmic material, yet here we were watching them being mass-produced in real time. The kilonova's brightness evolution followed a pattern that matched theoretical predictions with remarkable accuracy. Computer models had suggested that neutron star mergers should produce expanding clouds of radioactive debris files that would glow for weeks or months. As the unstable isotopes decayed, GW170817 provided the first direct confirmation of these decades-old theoretical predictions. But perhaps most remarkably, the kilonova was efficiently converting the kinetic energy of the expanding debris into light. The explosion was so energetic that it was literally glowing from the inside out, heated not by external energy sources, but by the radioactive decay of its own newly created elements. The expanding debris cloud itself was a marvel of extreme physics. Material ejected from the merger was traveling at speeds of up to 30,000 kilometers per second, roughly 10% the speed of light. At these velocities, the debris crossed distances equivalent to Earth's orbit around the Sun in just a few hours. As the weeks passed, astronomers watched the kilonova fade and evolve, but its scientific impact only grew. The light curves, vines showing how the brightness changed over time, provided detailed information about the masses of different elements being produced. By measuring how quickly the kilonova faded and how its color changed, scientists could calculate exactly how much gold, platinum, and other precious metals had been forged in the explosion. The results were staggering. The single kilonova event, GW170817, produced approximately 10 Earth masses of gold, more than 10,000 times all the gold that has ever been mined on our planet. It also created about 500 Earth masses of platinum and significant quantities of virtually every element heavier than iron. Dr. Brian Metzger, whose theoretical work had predicted many of the kilonova's properties years before GW170817 was detected, reflects on the discovery. We had spent decades working out the theory of kilonovae, but seeing it actually happen, watching our predictions play out in real time in a telescope, was profoundly moving. We were witnessing the universe's greatest act of creation through its most violent act of destruction. The kilonova emission from GW170817 continued to be detectable for months after the initial explosion, gradually fading as the radioactive fuel was exhausted and the debris cooled. But the scientific impact of this single event would resonate for decades, fundamentally changing our understanding of how the universe creates its most precious elements. The cosmic forge was in full operation, and humanity had a front-row seat to the greatest show in the universe. In the heart of the expanding kilonova debris, a cosmic alchemy is taking place that transforms the death of stars into the building blocks of planets, life, and civilization itself. The gold in your jewelry, the platinum in your car's catalytic converter, the uranium powering nuclear reactors. All of these elements share a common violent origin story. They were forged not in the steady nuclear furnaces of stars, but in the most extreme conditions the universe can create. The collision of neutron stars and the kilonova explosions that follow. For decades, astronomers had puzzled over what they called the heavy element problem. Stars are remarkably efficient at creating elements up to iron through nuclear fusion, the process that powers the sun and every other star in the universe. But iron represents a kind of cosmic dead end. Elements heavier than iron require more energy to create than they release through fusion, making them impossible to produce in stellar cores under normal conditions. Yet heavy elements clearly exist throughout the universe. Earth's crust contains gold, silver, harsh crust contains gold, silver, platinum, and dozens of other elements that stars shouldn't be able to make. The question that haunted astrophysicists was simple: where do these elements come from? The answer, revealed in dramatic detail by GW 170817, lies in understanding nucleosynthesis under the most extreme conditions imaginable, conditions that exist only in the aftermath of neutron star collisions. When two neutron stars merge, they create an environment unlike anywhere else in the modern universe. The collision ejects several Earth masses of neutron-rich matter at tremendous velocities, creating an expanding cloud of material with neutron densities millions of times higher than anything found in terrestrial laboratories. Under these conditions, atomic nuclei can capture neutrons at rates that would be impossible anywhere else. This is the rapid neutron capture process, the R process, and it's the universe's primary mechanism for creating elements heavier than iron. Dr. Anna Friebel, whose research focuses on the oldest stars in our galaxy, explains the process. In a kilonova, you have more free neutrons than atomic nuclei to capture them. It's like having a construction site with unlimited building materials and no time constraints. Nuclei can absorb neutron after neutron, building up to incredibly heavy elements before they have time to decay. The OR process works by overwhelming atomic nuclei with so many neutrons that they don't have time to undergo their normal radioactive decay. A typical iron nucleus, for example, contains 26 protons and 30 neutrons. But in the neutron-rich environment of a kilonova, that same iron nucleus might rapidly capture dozens of additional neutrons, creating unstable isotopes that would never exist under normal conditions. These neutron-heavy isotopes are profoundly unstable, but in the kilonova environment, they don't need to last long. Before they can decay, they capture even more neutrons, building up to elements with atomic numbers far exceeding anything that exists naturally on Earth. The process continues until the nuclei become so neutron-rich that they can't capture any more neutrons, at which point they begin a cascade of radioactive decay that transforms them into stable heavy elements. This decay process is what powers the kilonova's glow, as unstable isotopes decay into lighter, more stable elements. They release energy in the form of alpha particles, beta particles, and gamma rays. This energy heats the expanding debris cloud, causing it to glow with the brightness of hundreds of millions of suns. The specific elements created during the R process depend on the exact conditions in the kilonova, the neutron density, temperature, and expansion rate of the debris. Computer simulations suggest that a single neutron star merger can produce virtually every element heavier than iron, from cobalt and nickel up to the heaviest naturally occurring elements like uranium and thorium. The quantities involved are staggering. The kilonova from GW 170817 produced approximately 10 Earth masses of gold, 500 Earth masses of platinum, 500 Earth masses of platinum, several Earth masses, each of silver, palladium, and other precious metals, significant quantities of rare earth elements like europium and gadolinium, heavy actinides including uranium and thorium. To put this in perspective, the gold produced by this single event exceeds the total amount of gold in Earth's crust by a factor of more than 100. If you could somehow collect all the gold created by GW 170817, it would be enough to coat the entire surface of Earth in a layer several centimeters thick, at times so meters thick. But the Ribber process doesn't just create heavy elements, it creates them in specific ratios that match what we observe in the oldest stars in our galaxy. This provides compelling evidence that kilonovae have been the primary source of heavy elements throughout cosmic history. Dr. Enrico Ramirez Ruiz, whose simulations have mapped the Roll process in unprecedented detail, describes the significance. We're not just talking about element creation on a massive scale. We're talking about the process that made complex chemistry possible in the universe. Without the Roll process in kilonovae, there would be no heavy elements, no rocky planets, and no life as we know it. The heavy elements created in kilonovae don't remain confined to the explosion site. The tremendous velocities involved, up to 30,000 kilometers per second, carry these newly forged elements far from their birthplace, enriching the surrounding interstellar medium with the raw materials for future generations of stars and planets. This cosmic recycling process has been operating for billions of years. Every kilonova explosion scatters heavy elements across vast regions of space, where they eventually become incorporated into new star-forming regions. When these enriched gas clouds collapse to form new stars, they create planetary systems that contain the full range of elements necessary for complex chemistry and potentially life. The gold atoms in your wedding ring, the silver in your electronics, the rare earth elements in your smartphone, all were created in kilonova explosions that occurred billions of years ago, then traveled through space for eons before becoming incorporated into the solar nebula that eventually formed our solar system. As we'll see, this cosmic alchemy represents one of the universe's most profound paradoxes. The most violent events in nature are also the most creative, transforming stellar death into the seeds of future worlds and the building blocks of life itself. The rapid neutron capture process, known to physicists as the R process, is one of nature's most elegant solutions to a seemingly impossible problem: how to build atomic nuclei heavier than iron when the universe actively resists their creation. Under normal stellar conditions, creating elements heavier than iron is like trying to push water uphill. Each additional proton or neutron you add to an iron nucleus requires more energy input than the nucleus can provide through fusion reactions. This is why stars burn out when their cores become dominated by iron. They've reached the end of the nuclear fuel chain that can sustain them against gravitational collapse. But the Ra process takes a completely different approach. Instead of trying to build heavier elements by fusing lighter ones together, the slow, energy-intensive process that powers stars, the Ra process overwhelms existing nuclei with so many neutrons that they have no choice but to grow heavier. Dr. Rebecca Sermon, whose research focuses on R process nucleosynthesis, explains the fundamental difference in stars. You're trying to convince nuclei to accept new particles by giving them energy. In the R process, you have so many neutrons available that nuclei capture them faster than they can decide whether they want them or not. The key to understanding the R process lies in appreciating just how neutron-rich the environment inside a kilonova becomes. In normal matter, neutrons and protons exist in roughly equal numbers, bound together in atomic nuclei. But when neutron star matter is ejected during a merger, it creates conditions where free neutrons outnumber protons by factors of hundreds or even thousands. Under these conditions, atomic nuclei become like magnets dropped into a sea of iron filings. They capture neutron after neutron in rapid succession, becoming increasingly neutron-heavy with each capture. The process happens so quickly that even highly unstable isotopes don't have time to decay before capturing additional neutrons. This creates what physicists call neutron-rich nuclei, atomic configurations that are so far from stability that they would decay in microseconds under normal conditions. But in the R-process environment, these unstable nuclei serve as stepping stones to even heavier elements, capturing more neutrons before they have time to decay. The R process follows what's known as the neutron drip line, the theoretical boundary beyond which atomic nuclei cannot hold any more neutrons. As nuclei approach this boundary, they become increasingly unstable, but they also become capable of producing the heaviest elements in the universe when they finally do decay. When the neutron bombardment finally ends, as the kilonova debris expands and cools, reducing the neutron density, the unstable isotopes begin their inevitable decay. But this decay doesn't simply destroy the heavy elements that were created. Instead, it transforms them into stable isotopes of heavy elements through a cascade of radioactive decay processes. A typical R-process decay chain might begin with an extremely neutron-rich isotope of a super-heavy element that doesn't even have a name, through a series of beta decays, where neutrons transform into protons by emitting electrons. This unstable isotope gradually works its way down to stable isotopes of elements like gold, platinum, or uranium. The beauty of the R process is that it can create virtually every element heavier than iron simultaneously. Unlike stellar nucleosynthesis, which tends to favor certain elements over others, depending on the star's mass and evolutionary stage, the R process creates heavy elements in ratios that remain remarkably consistent across different kilonova events. In canon, this dura nu, in theae, in keviutheoneae. This consistency has provided astronomers with a powerful diagnostic tool by measuring the relative abundance of different heavy elements in ancient stars. They can trace the Ra process enrichment history of our galaxy and determine how frequently kilonova events have occurred throughout cosmic time. The Ra process also explains one of the most puzzling observations in astronomy: why the oldest stars in our galaxy contain heavy elements at all. These ancient stars formed when the universe was less than 1 billion years old, long before most stars had completed their life cycles and exploded as supernova, yet they contain detectable amounts of gold, platinum, and other R-process elements. The only way these elements could have existed so early in cosmic history is if they were created by processes that operated on much shorter timescales than stellar evolution. Kilonovae, which can occur whenever two massive stars in a binary system both undergo core collapse, a process that can happen in just a few 100 million years, provide exactly the kind of rapid, heavy element enrichment needed to explain these observations. Dr. John Cowan, who has spent decades studying R-process elements in ancient stars, describes the breakthrough, the kilonova detection from GW 1708. 17 finally gave us the smoking gun we needed. We could see the R process happening in real time, creating exactly the elements we observe in the oldest stars in our galaxy. The R process revealed by GW 1708. 17 represents more than just exotic nuclear physics. It's the mechanism that made complex chemistry possible in the universe. Without the rapid neutron capture process operating in kilonovae, the cosmos would be a much simpler and much more sterile place. As we'll see, this cosmic element factory has been operating for billions of years, gradually enriching the universe with the heavy elements that make rocky planets, complex molecules, and ultimately life itself possible. The story of heavy element creation doesn't end with the R process. It begins there. The real cosmic significance of kilonovae lies not just in their ability to create gold and platinum, but in their role as the universe's primary distribution system for heavy elements. When a kilonova explodes, it doesn't simply create heavy elements and hold onto them. The tremendous energy of the explosion accelerates the newly forged material to speeds of up to 30,000 kilometers per second, roughly 10% the speed of light. At these velocities, the enriched debris escapes not just the immediate explosion site, but often the gravitational pull of the host galaxy itself. This cosmic dispersal process operates on scales that dwarf anything we experience on Earth. The heavy elements created in a single kilonova event can travel for millions of years, crossing distances measured in thousands of light years, before they finally slow down and mix with the interstellar medium. Dr. Daniel Casson, whose simulations have tracked the long-term evolution of kilonova debris, explains the scale. A single kilonova can enrich a volume of space larger than our entire local group of galaxies. The heavy elements from one neutron star merger can provide the raw materials for thousands of future planetary systems. This dispersal process has been operating throughout cosmic history, gradually transforming the chemical composition of the universe. In the early cosmos, shortly after the Big Bang, only the lightest elements, hydrogen, helium, and traces of lithium existed. Everything else had to be created by stars and stellar explosions. Kilonovae represent the most efficient heavy element factories in the universe. While supernovae also create and distribute heavy elements, they tend to destroy as many heavy elements as they create through the violence of their explosions. Kilonovae, by contrast, are pure creators. They synthesize heavy elements without destroying pre-existing ones. The impact of this cosmic seeding can be traced in the chemical evolution of galaxies. Astronomers have found that galaxies with higher rates of neutron star mergers tend to have higher concentrations of R process elements like europium and gold. This provides direct evidence that kilonovae are indeed the primary source of these elements on galactic scales. But the influence of kilonova enrichment extends far beyond simple element abundances. The heavy elements distributed by these explosions are essential for the formation of rocky planets. Elements like silicon, magnesium, and iron, created in stellar cores and distributed by supernova, can form basic rocky material. But the complex chemistry that makes planets geologically active requires heavier elements that can only be created through the raw process. The rare earth elements produced in kilonovae, for example, are crucial for creating the kinds of complex minerals that store heat in planetary interiors and drive geological processes like plate tectonics. Without these elements, Earth would likely be a geologically dead world, incapable of maintaining the dynamic surface processes that have kept our planet habitable for billions of years. The cosmic recycling process works on timescales that span billions of years. Heavy elements ejected by ancient kilonovae gradually mix with the interstellar medium, becoming incorporated into molecular clouds that eventually collapse to form new generations of stars. These enriched stars can then form planetary systems that contain the full periodic table of elements. Our own solar system is a product of this cosmic enrichment process. The gold in Earth's core, the platinum group elements that make catalytic reactions possible, the uranium that provides heat through radioactive decay, all were created in kilonova explosions that occurred billions of years before our solar system formed. But perhaps most remarkably, the heavy elements distributed by kilonovae may be essential for life itself. Many biological processes depend on trace amounts of heavy elements that can only be created through the raw process. The molybdenum in certain enzymes, the rare earth elements that some organisms use for specialized functions, even the radioactive elements that provide geothermal energy, all trace their origins back to neutron star collisions. This creates a profound connection between the most violent events in the universe and the existence of life. Every atom in your body, heavier than iron, was forged in the cosmic violence of a kilonova explosion, then traveled through space for billions of years before becoming part of the solar nebula that eventually formed Earth and everything on it. The universe's greatest acts of destruction are simultaneously its most profound acts of creation, scattering the seeds of future worlds and the building blocks of life across the cosmos with each spectacular explosion. The detection of GW170817 transformed theoretical astrophysics into observational reality. But it also launched the greatest detective story in modern astronomy, a cosmic investigation that would confirm decades of theoretical predictions with unprecedented precision. For over 40 years, astrophysicists had been building theoretical models of what should happen when two neutron stars collide. These models, based on Einstein's general relativity and our understanding of nuclear physics, painted a picture of cosmic violence so extreme that it seemed almost too spectacular to be real. The collision should produce gravitational waves, gamma-ray bursts, and kilonova explosions that would scatter freshly forged heavy elements across space. But until August 17, 2017, these remained theoretical predictions, elegant mathematical models that had never been tested against reality. Dr. Chris Fryer, who spent decades developing kilonova models, describes the anticipation. We had built these incredibly detailed theoretical frameworks, but there was always the nagging question: what if we're wrong? What if nature works differently than our equations predict? GW 170817 was the moment of truth. The first clue came from the gravitational wave signal itself. LIGO and Virgo detected exactly the kind of chirp that binary neutron star simulations had predicted, a signal that started at low frequencies and swept upward as the neutron stars spiraled closer together. The way the frequency increased, the rate at which the amplitude grew, even the precise timing of the final merger, all matched theoretical expectations with remarkable accuracy. But gravitational waves alone couldn't tell the complete story. The real detective work began when the Fermi Gamma Ray Space Telescope detected GRB 170817A just 1.7 seconds after the gravitational wave signal ended. This tiny time delay immediately provided crucial information about the fundamental nature of the universe itself. Einstein's general relativity predicts that gravitational waves should travel at exactly the speed of light. But this prediction had never been tested directly over cosmic distances. The 1.7-second delay between the gravitational wave detection and the gamma-ray burst, traveling from the same source, 130 million light-years away, confirmed Einstein's prediction with extraordinary precision. The speed of gravitational waves matched the speed of light to within 1 part in a quadrillion. This seemingly simple observation had profound implications. It ruled out entire classes of alternative theories of gravity that predicted gravitational waves should travel at different speeds. With a single detection, GW 170817 eliminated decades of speculative physics and confirmed that Einstein's century-old theory remains our best description of how gravity works on cosmic scales. The next piece of evidence came from the optical telescopes that spotted the kilonova glow in galaxy NGC 4993. The light curve, how the brightness changed over time, followed theoretical predictions with stunning accuracy. Computer models had suggested that kilonova explosions should peak in brightness within a day or two, then fade exponentially as radioactive elements decayed. The observations showed exactly this behavior. Even more remarkable was the color evolution of the kilonova. Theoretical models predicted that the expanding debris should start blue, dominated by lighter elements like iron and nickel, then shift to red and infrared as heavier lanthanide elements began to dominate the emission. The observations followed this predicted sequence precisely, providing direct confirmation that heavy elements were being created through the R process. Dr. Brian Metzger, whose theoretical work had predicted many of kilonova properties years before the detection, reflects on seeing theory become reality. It was surreal to watch our computer simulations playing out in real telescopes. The light curves, the color evolution, the spectral features, everything matched our predictions so closely that it was almost eerie. The spectroscopic analysis provided the most detailed forensic evidence. When astronomers broke down the kilonova's light into its component wavelengths, they found the fingerprints of elements that had been created just hours or days earlier. The absorption lines in the spectrum matched laboratory measurements of heavy elements like strontium, yttrium, and lanthanides, direct proof that the raw process was operating exactly as theory predicted. Perhaps most importantly, the kilonova observations solved quantitative puzzles that had persisted for decades. By measuring how much light the kilonova produced and how it faded over time, astronomers could calculate exactly how much radioactive material had been created in the explosion. The answer, about 0.05 solar masses of material, matched theoretical predictions for neutron star mergers almost perfectly. The heavy element abundances observed in the kilonova also matched what astronomers see in ancient stars throughout our galaxy. This provided compelling evidence that neutron star mergers have been the primary source of R-process elements throughout cosmic history, solving the decades-old mystery of where heavy elements come from. But the detective story didn't end with confirming existing theories. GW 170817 also revealed new mysteries that are still being investigated. The gamma-ray burst was weaker than expected. The kilonova was brighter in infrared light than some models predicted. And the long-term evolution of the explosion showed unexpected features that are pushing theoretical models to their limits. Each new observation added another piece to the cosmic puzzle, building a comprehensive picture of neutron star mergers that exceeded even the most optimistic expectations of theoretical astrophysicists. The universe had provided the ultimate test of our understanding, and our theories had passed with flying colors. GW 170817 didn't just confirm theoretical predictions, it inaugurated an entirely new era of astronomy, one where scientists study cosmic events using multiple messengers that carry information across the universe in fundamentally different ways. For most of human history, astronomy was limited to studying light, electromagnetic radiation in its various forms. First visible light, captured by the naked eye, and later by telescopes. Then radio waves, infrared radiation, ultraviolet light, X-rays and gamma rays as technology advanced. Each new form of electromagnetic radiation opened new windows on the universe, revealing phenomena that were invisible in other wavelengths. But electromagnetic radiation, for all its variety, represents just one type of cosmic messenger. Photons can be absorbed, scattered, or blocked by intervening matter, sometimes hiding the most energetic events behind veils of dust and gas. They also carry information only about the surfaces of objects, the last place the photons interacted before beginning their journey to Earth. Gravitational waves represent a fundamentally different type of messenger. They carry information about the acceleration of mass itself, passing through matter as if it were transparent. A gravitational wave that began its journey in the heart of a neutron star merger carries unfiltered information about that event across billions of light-years of space, arriving at Earth with its message intact. Dr. Gabriela Gonzalez, who served as spokesperson for the LIGO scientific collaboration during the GW 170817 detection, explains the revolutionary nature of multi-messenger astronomy. It's like the difference between seeing a concert and hearing it. Electromagnetic radiation lets us see the universe, but gravitational waves let us hear it. When you combine both senses, you get a much richer understanding of what's happening. The detection of GW 170817 required unprecedented coordination between gravitational wave observatories and electromagnetic telescopes around the world. Within minutes of LIGO and Virgo detecting the gravitational wave signal, automated alert systems notified thousands of astronomers that something extraordinary had been detected. The gravitational wave data provided crucial information about the location of the source, narrowing down the possible position to a region of sky covering just 28 square degrees. This might sound like a large area, but in astronomical terms, it's remarkably precise. For comparison, the full moon covers only about 0.2 square degrees of sky. Armed with this location information, telescope operators around the world began the largest coordinated search in astronomical history. All within 11 hours, the SWOPE supernova survey had identified the optical counterpart in galaxy NGC 4993. Within days, over 70 telescopes and observatories were studying the kilonova across the entire electromagnetic spectrum. This coordination revealed information that neither gravitational waves nor electromagnetic radiation could provide alone. The gravitational waves told astronomers about the masses and orbital evolution of the neutron stars, while the electromagnetic observations revealed what happened after the collision, the creation of heavy elements, the formation of relativistic jets, and the long-term evolution of the expanding debris. The multi-messenger approach also provided redundant confirmation of key measurements. The distance to the source, for example, could be calculated independently from both the gravitational wave amplitude and the brightness of the kilonova. Both methods gave the same answer, 130 million light-years, providing confidence that astronomers were indeed observing the same event through different cosmic messengers. Perhaps most remarkably, the multi-messenger observations of GW 170817 provided the first direct measurement of the Hubble constant, the rate at which the universe is expanding, using gravitational waves. Wonderdires and Wave Sing Vuren. So, this independent measurement helps resolve ongoing debates about the precise value of this fundamental cosmological parameter. The success of multi-messenger astronomy with GW 170817 has transformed how astronomers approach cosmic events. Future gravitational wave detections are now automatically followed up with coordinated electromagnetic observations, creating a global network of instruments working together to study the universe's most violent events. Dr. Mansi Kasliwal, who led one of the first electromagnetic follow-up campaigns, describes the transformation. GW 170817 showed us that the universe is far richer than we realized when we were limited to studying it with just one type of messenger. Multi-messenger astronomy isn't just a new technique, it's a new way of understanding the cosmos. The multi-messenger revolution launched by GW 170817 is still in its infancy. Future detections promise to reveal even more about neutron star mergers, black hole formation, and the fundamental nature of matter under extreme conditions. The universe has many more stories to tell, and now humanity has the tools to hear them all. Within months of the GW 170817 detection, astrophysics textbooks around the world became obsolete. The single most important astronomical discovery of the 21st century had fundamentally changed our understanding of neutron stars, heavy element creation, and the violent processes that shape the cosmos. The immediate impact was felt in multiple fields simultaneously: nuclear physics, stellar evolution, galactic chemical evolution, gravitational wave astronomy, and cosmology all had to incorporate new insights from this single extraordinary event. Perhaps nowhere was the revolution more dramatic than in our understanding of heavy element nucleosynthesis. For decades, astrophysicists had debated the relative contributions of different processes to the creation of elements heavier than iron. Supernovae were known to create some heavy elements, but computer models struggled to explain the observed abundances of R process elements like gold, platinum, and uranium. The RA process requires such extreme neutron densities that many scientists doubted whether the necessary conditions could ever exist in nature. Some theoretical models suggested that rare types of supernovae might be capable of ore process nucleosynthesis, while others pointed to neutron star mergers as the most likely sites. But without direct observational evidence, the debate remained unresolved. GW 170817 settled the question definitively. The kilonova observations provided direct, spectroscopic evidence of R process nucleosynthesis occurring in real time. The heavy elements detected in the expanding debris, strontium, yttrium, lanthanides, and likely gold and platinum, could only have been created through rapid neutron capture in the extreme environment of a neutron star merger. Dr. Enrico Ramirez Ruiz, whose research group had long advocated for neutron star mergers as the primary R process sites, describes the vindication. For years, we had been arguing that kilonovae were the answer to the heavy element puzzle based on theoretical grounds. GW 170817 gave us the observational proof we needed. The case was closed. The discovery also resolved the long-standing mystery of why R process elements appear in such consistent ratios throughout the galaxy. Unlike supernovae, which produce different element ratios depending on the progenitor star's mass and metallicity, neutron star mergers create heavy elements in remarkably uniform proportions. This explains why ancient stars throughout the Milky Way show similar R process abundance patterns, despite forming in different regions of the galaxy. But the textbook revisions extended far beyond nuclear astrophysics. The gravitational wave detection provided the first direct confirmation that binary neutron star systems exist and evolve exactly as general relativity predicts. This validated decades of theoretical work on gravitational wave emission and orbital decay, while simultaneously opening new avenues for testing Einstein's theory under the most extreme conditions. The precise timing between the gravitational wave detection and the gamma-ray burst also had profound implications for fundamental physics. The 1.7-second delay between these signals, traveling from the same source 130 million light-years away, placed extraordinary constraints on theories that attempt to modify Einstein's general relativity. Any theory predicting that gravitational waves travel at speeds different from light was immediately ruled out. Dr. Clifford Will, whose research focuses on testing general relativity, explains the significance. GW 170817 provided one of the most stringent tests of Einstein's theory ever performed. The fact that gravitational waves and light arrived within 1.7 seconds of each other after traveling for 130 million years confirmed that both travel at the same speed to within 1 part in a quadrillion. The discovery also revolutionized our understanding of short gamma-ray bursts. These brief, intense flashes of high-energy radiation had been observed for decades, but their physical origin remained mysterious. The association of GRB 170817A with the neutron star merger, HREIT, provided definitive proof that at least some short gamma-ray bursts are produced by colliding neutron stars. Hello, interledenated. With the neutron straws what it had never applied vis straw. This connection solved several puzzles about gamma-ray burst properties. The relatively low luminosity of GRB 170817A, its unusual spectrum, and its association with an old elliptical galaxy made sense once astronomers realized they were seeing a gamma-ray burst from the side rather than looking directly down the relativistic jet. The kilonova detection also had immediate implications for cosmology. By combining the distance measurement from gravitational waves with the recession velocity of the host galaxy, astronomers obtained an independent measurement of the Hubble constant, the rate of cosmic expansion. This standard siren approach to cosmology promised to help resolve ongoing debates about the universe's expansion rate. Educational institutions around the world scrambled to update their curricula. Courses on stellar evolution had to incorporate new sections on binary neutron star evolution and kilonova explosions. Nuclear physics classes began discussing ray process nucleosynthesis as an observed phenomenon rather than a theoretical possibility. Gravitational wave astronomy, which had been a niche specialty just a few years earlier, became a mainstream field requiring coverage in introductory astronomy courses. The pace of discovery accelerated rather than slowed after GW 170817. Each new gravitational wave detection brought the possibility of another electromagnetic counterpart, another opportunity to study cosmic violence through multiple messengers. The techniques developed for following up GW 170817 became standard protocols applied to every subsequent gravitational wave event. Dr. Julie McHenry, whose team coordinated much of the electromagnetic follow-up observations, reflects on the transformation. GW 17 changed everything about how we study transient astronomical phenomena. It showed us that the universe is far more dynamic and interconnected than we realized, and it gave us the tools to study that dynamism in unprecedented detail. The textbooks would need to be rewritten again and again as the multi-messenger revolution continued to unfold. In the smoking aftermath of the most violent collision since the Big Bang, the fundamental question haunts astronomers: what cosmic entity could possibly survive such catastrophic violence? The merger of two neutron stars doesn't simply destroy both objects. It transforms them into something new, something that pushes the very boundaries of what matter can become under the influence of gravity. But determining exactly what emerges from this cosmic crucible has proven to be one of the most challenging puzzles in modern astrophysics. The immediate product of the collision is what physicists call a hypermassive neutron star. An object that contains more mass than any stable neutron star should theoretically be able to support. These objects exist in a precarious state, held up not by the neutron degeneracy pressure that stabilizes normal neutron stars, but by their rapid rotation and the intense heat generated by the merger. Dr. Luciano Rezzola, whose computer simulations have probed the post-merger dynamics in unprecedented detail, describes the challenge. We're trying to understand an object that exists at the absolute limit of what physics allows. It's more massive than any neutron star we've ever observed, spinning faster than any pulsar and hotter than the core of any star. It's unlike anything else in the universe. The hypermassive neutron star created by GW 170817 likely survived for anywhere from a few milliseconds to several minutes after the collision, an incredibly brief existence by astronomical standards, but long enough to fundamentally alter the surrounding environment. During this time, it acted like a cosmic engine, powering the gamma-ray burst and helping to accelerate the expanding kilonova debris to tremendous velocities. In so to be said, but the hypermassive state is inherently unstable. As the object loses energy through gravitational wave emission and neutrino radiation, it gradually slows its rotation and cools. When the rotational support and thermal pressure are no longer sufficient to counteract gravity, the hypermassive neutron star faces an inevitable collapse. The final fate depends critically on the total mass of the system. If the combined mass of the two original neutron stars was below about 2.8 times the mass of our Sun, the hypermassive neutron star might shed enough material and angular momentum to become a stable, albeit unusually massive neutron star. Such objects would represent the most extreme neutron stars in the universe, cosmic laboratories where matter exists under conditions that push the fundamental forces to their limits. However, if the total mass exceeds this critical threshold, as appears to be the case for GW 170817, when this happens, the hypermassive neutron star disappears behind an event horizon, taking with it direct information about the ultra-dense matter it contained. The formation of a black hole from neutron star merger debris creates what astronomers call a stellar mass black hole, with properties unlike those formed from single-star collapse. These merger remnant black holes typically have masses between 2.5 and 5 times that of our Sun, filling in a mysterious mass gap in the black hole population that had puzzled astronomers for years. Determining which fate befell GW 170817 requires detective work that extends far beyond the initial observations. If a stable neutron star formed, it should eventually become observable as a pulsar, rapidly rotating neutron star that sweeps beams of radiation across space like a cosmic lighthouse. But if a black hole formed, the merger remnant would be much more difficult to detect directly. Dr. Ben Margalit, whose research focuses on post-merger dynamics, explains the observational challenge. We're looking for subtle signatures in the kilonova emission that might tell us whether the central engine is a neutron star or a black hole. It's like trying to diagnose the health of an engine by examining its exhaust fumes. Recent analysis of the long-term evolution of GW 170817 suggests that a black hole likely formed within a few hundred milliseconds of the merger. The specific way the kilonova emission evolved over months, combined with the absence of any detectable pulsar signals from the merger site, points toward black hole formation as the most probable outcome. This conclusion has profound implications for our understanding of neutron star physics. It suggests that there is indeed an upper limit to how massive neutron stars can become, a fundamental boundary beyond which matter cannot resist the inexorable pull of gravity. The remnant of GW 170817, whether it's an ultra-massive neutron star or a stellar mass black hole, continues to influence its surroundings long after the initial violence has subsided. Understanding what remains is crucial for predicting the long-term evolution of the expanding debris and its ultimate impact on the surrounding galaxy. While astronomers debate the nature of the central remnant, The expanding shockwave from GW1708-17 continues its relentless journey outward, carrying the signature of cosmic violence across increasingly vast regions of space. The kilonova explosion didn't create a single uniform blast wave. Instead, it launched multiple components of debris at different velocities and in different directions, creating a complex, evolving structure that astronomers are still working to understand. The fastest moving material, the relativistic jets that produce the gamma-ray burst, raced outward at nearly the speed of light, carving narrow channels through the surrounding medium. These jets, just a few degrees wide, carried tremendous energy, but affected only a tiny fraction of the space around the merger site. More significant for the long-term evolution of the system was the dynamical ejector material that was torn away from the neutron stars during the final moments of the merger and flung into space at velocities of 10,000 to 30,000 kilometers per second. This debris, enriched with freshly synthesized heavy elements, forms an expanding shell that grows larger and more diffuse with each passing day. But the most massive component of the explosion was the wind ejector material blown away from the accretion disk that surrounded the merger remnant. This component, moving at somewhat lower velocities of a few thousand kilometers per second, actually contains more mass than the faster-moving dynamical ejector and plays a crucial role in the kilonova's long-term evolution. Dr. Jennifer Barnes, whose research focuses on kilonova modeling, describes the complexity. We're not dealing with a simple spherical explosion like a supernova. The kilonova ejector has a complex three-dimensional structure with different components moving at different speeds in different directions. It's like trying to understand a cosmic firework that's still exploding. As the expanding debris encounters the interstellar medium surrounding the merger site, it creates shockwaves that heat the ambient gas and accelerate particles to high energies. These shocks generate what astronomers call afterglow emission, a long-lived source of radiation that can remain detectable for years or even decades after the initial explosion. The afterglow from GW1708-17 has provided astronomers with a unique laboratory for studying how kilonova debris interacts with its environment. Observations across the electromagnetic spectrum, from radio waves to X-rays, have revealed the detailed structure of the expanding shockwave and provided insights into the properties of both the ejector and the surrounding medium. One of the most remarkable discoveries from the afterglow observations was the detection of superluminal motion, the appearance that parts of the expanding debris are moving faster than the speed of light. This isn't a violation of Einstein's relativity, but rather an optical illusion that occurs when material moving at near light speed travels almost directly toward Earth. The effect provided additional confirmation that the kilonova had indeed produced relativistic jets. The expanding shockwave also reveals information about the environment surrounding the merger site. The way the afterglow brightens and fades depends on the density of the interstellar medium, providing astronomers with a way to probe the space around the neutron stars before they collided. Surprisingly, the observations suggest that the merger occurred in a relatively sparse environment, a region of space with gas densities much lower than typical interstellar values. This finding has implications for understanding how binary neutron star systems evolve and where they're most likely to merge. Dr. Tanmoy Lasker, who has led long-term monitoring of the GW1708-17 afterglow, explains the significance. The afterglow is like a cosmic CT scan that reveals the three-dimensional structure of the explosion and its environment. We can literally see how the shockwave is expanding and interacting with the surrounding space. The expanding debris from GW1708-17 will continue to evolve for decades to come. As the shockwave slows and cools, different physical processes will dominate the emission, creating an evolving laboratory for studying extreme astrophysics. The heavy elements carried by the expanding shell will eventually mix with the interstellar medium, enriching the surrounding space with gold, platinum, and other R-process elements. This enrichment process operates on timescales of thousands to millions of years, gradually increasing the heavy element content of the region around the merger site. Computer simulations suggest that the expanding bubble of enriched material will eventually reach sizes of hundreds of light-years across, affecting star formation in the surrounding region for millions of years to come. Future generations of stars that form from this enriched material will have higher concentrations of heavy elements, potentially making them more likely to form rocky planets capable of supporting complex chemistry. The shockwave itself will eventually fade as it expands and cools, but its influence on the surrounding galaxy will persist for eons. The kinetic energy deposited by the expanding debris helps to heat and stir the interstellar medium, contributing to the complex dynamics that govern galactic evolution. Years after the initial detection, GW170817 continues to teach us about the long-term consequences of cosmic violence. The expanding shockwave serves as a persistent reminder that the most energetic events in the universe have effects that persist long after the initial explosion fades from view. The aftermath of this cosmic collision will continue to unfold for millions of years, carrying the signature of violence and creation across the galaxy. As months turn to years following the detection of GW170817, astronomers witness something both beautiful and melancholy: the gradual fading of the universe's most violent explosion into cosmic silence. The kilonova that had blazed with the light of 200 million suns began its inevitable decline, following the inexorable laws of physics as the radioactive fuel that powered its brilliance slowly exhausted itself. But this wasn't simply a matter of lights going out. The fading kilonova was revealing new secrets about the nature of cosmic violence and the long-term fate of the heavy elements it had created. The decline followed a pattern that astronomers had predicted but never before observed in nature. The kilonova's brightness decreased exponentially, with a half-life determined by the radioactive decay of the unstable isotopes created during the R process. Initially powered by the decay of nickel-56 and cobalt-56, the same isotopes that fuel supernova light curves, the emission gradually shifted to longer-lived radioactive elements as the lighter isotopes were exhausted. Dr. Ariadna Murgia-Berthia, whose team monitored the kilonova's evolution over months, describes the process. We were watching the universe's most exotic nuclear reactor slowly burning through its fuel. Each element that decayed away revealed new layers of the explosion, like peeling back the pages of a cosmic story written in radioactive ink. The color evolution during this fading process was equally remarkable. As the expanding debris cooled and became more transparent, different elements began to dominate the emission. The blue light of the early kilonova, dominated by iron peak elements, gave way to red and infrared emission from heavier lanthanides and actinides. This spectral evolution provided astronomers with a unique opportunity to study the detailed composition of our process material. By tracking which wavelengths of light were absorbed and emitted as the kilonova faded, they could map the distribution of different elements within the expanding debris cloud. The observations revealed a complex, three-dimensional structure that challenged simple models of kilonova emission. The debris wasn't uniformly mixed. Instead, it showed clear signs of stratification, with different elements concentrated in different regions of the expanding shell. Lighter R process elements appeared to be concentrated in the fastest-moving parts of the ejector, while the heaviest elements were found in the slower, more massive components. As the kilonova faded below the detection threshold of optical telescopes, astronomers turned to longer wavelengths to continue monitoring its evolution. Radio observations revealed the ongoing interaction between the expanding debris and the surrounding interstellar medium, while infrared telescopes caught the last glimmers of thermal emission from the cooling ejector. The transition from optical to infrared emission marked a fundamental change in the nature of the kilonova. No longer powered primarily by radioactive decay, the emission was now dominated by thermal radiation from dust grains that had condensed within the cooling debris. This dust formation represented yet another way that kilonova explosions contribute to the cosmic ecosystem, not only creating heavy elements, but processing them into the solid particles that will eventually become incorporated into future planetary systems. Dr. Masaomi Tanaka, whose models predicted the late-time evolution of kilonova emission, explains the significance. The formation of dust in kilonova ejecta represents the final step in the element creation process. The heavy elements created in the R process are transformed into solid grains that can survive for billions of years, carrying the signature of their violent birth across the galaxy. The fading of GW 170817 also revealed important information about the central engine powering the explosion. The specific way the light curve evolved provided clues about whether the merger remnant was a neutron star or a black hole, and how long it survived before final collapse. By comparing the observed light curve with theoretical models, astronomers concluded that the merger likely produced a short-lived hypermassive neutron star that collapsed to form a black hole within a few hundred milliseconds. This conclusion was supported by the absence of any detectable pulsar emission from the merger site. If a stable neutron star had formed, it should eventually have become visible as a rotating pulsar. As the kilonova faded to invisibility in optical light, it left behind a changed region of space. The expanding bubble of heavy element-enriched material continued to grow, mixing with the surrounding interstellar medium and altering its chemical composition. This enrichment will persist for millions of years, affecting future generations of star formation in the region. The late-time evolution of GW 170817 also provided crucial calibration for future kilonova studies. By tracking how a kilonova fades and evolves over timescales of months to years, astronomers developed the tools needed to recognize and study similar events detected by future gravitational wave observations. Perhaps most poignantly, the fading of GW 170817 marked the end of humanity's first detailed observation of a kilonova explosion. The event that had captivated the astronomical community and revealed fundamental truths about the universe gradually slipped below the detection threshold of even the most sensitive instruments. But the scientific legacy of GW 170817 will persist long after its light has faded. The detailed observations of its birth, evolution, and eventual decline have provided a Rosetta Stone for understanding cosmic violence and element creation. Every future kilonova detection will be compared against this benchmark event, and the lessons learned from its fading echo will guide astronomers for decades to come. The universe's most violent explosion had spoken its final words, but its message will resonate through astronomy for generations. The story of GW 170817 extends far beyond a single violent event. It represents our first direct observation of the universe's most sophisticated recycling program, a cosmic process that transforms stellar death into the building blocks of future worlds and life itself. Every element heavier than lithium in the periodic table was created inside stars or during stellar explosions. Unlike the factory production lines of human industry, cosmic element creation operates on a scale and timeline that spans billions of years and millions of light-years. Kilonovae, like GW 170817, represent the most dramatic episodes in this ongoing cosmic recycling program. The process begins with the deaths of massive stars. When stars at least 8 times more massive than our Sun exhaust their nuclear fuel, they undergo core collapse, a catastrophic implosion that can forge a neutron star in less than a second. If 2 such massive stars exist in a binary system, both can undergo this transformation, creating a binary neutron star system destined for eventual collision. But the real recycling magic happens during the kilonova explosion itself. The neutron stars that collide contain matter that has been locked away from the rest of the universe for millions or even billions of years. This matter, compressed to nuclear densities and isolated behind the neutron star's enormous gravitational fields, is suddenly liberated and transformed through the Ra process into the heaviest elements in the periodic table. Dr. Anna Frebel, whose research focuses on chemical evolution in the early universe, explains the cosmic significance. Kilonovae are the universe's most efficient recycling centers. They take matter that was effectively removed from circulation when massive stars collapsed, process it into elements that couldn't be created any other way, and redistribute it across vast regions of space for future use. The efficiency of this recycling process is staggering. A single kilonova event like GW170817 can create more gold than would be produced by thousands of typical supernovae. The explosion ejects this freshly minted material at velocities of up to 30,000 kilometers per second, carrying it far from the explosion site and mixing it with the surrounding interstellar medium. This mixing process operates on multiple scales simultaneously. On the smallest scales, turbulence and instabilities in the expanding debris help to homogenize the composition of the ejector, ensuring that different heavy elements are thoroughly mixed together. On intermediate scales, the expanding shockwave from the kilonova creates cavities hundreds of light-years across, stirring and heating the interstellar medium. On the largest scales, multiple kilonova explosions over cosmic time have gradually enriched entire galaxies with R-process elements. The cosmic recycling program operates with remarkable efficiency across different types of galaxies. In massive elliptical galaxies, where star formation occurred primarily in the early universe, the heavy element abundance patterns reflect the cumulative effects of many ancient kilonova explosions. In smaller dwarf galaxies, individual kilonovae can have dramatic effects on the overall chemical composition, sometimes doubling or tripling the abundance of R-process elements in a single event. In the single event, computer simulations of galactic chemical evolution have shown that kilonovae are not just important contributors to heavy element production, they're absolutely essential. Without neutron star mergers, galaxies would contain only a tiny fraction of their observed R-process elements. The gold, platinum, and rare earth elements that we observe throughout the cosmos simply couldn't exist in their current abundances without the cosmic recycling program operating through kilonova explosions. But the recycling process extends far beyond just creating and distributing heavy elements. The energy deposited by kilonova explosions helps to regulate star formation in their host galaxies. The expanding shockwaves heat and compress surrounding gas clouds, sometimes triggering new episodes of star formation, while simultaneously making other regions too hot and turbulent for stars to form. This feedback mechanism creates a complex interplay between stellar death and stellar birth. The heavy elements produced by one generation of neutron star collisions become incorporated into the next generation of stars, creating a cosmic family tree where the composition of new stars reflects the violent history of their galactic neighborhood. The timescales involved in cosmic recycling are almost incomprehensibly long. The heavy elements ejected by GW170817 will continue expanding and mixing with the interstellar medium for thousands of years. Over millions of years, this enriched material will become incorporated into molecular clouds that eventually collapse to form new stars and planetary systems. The entire cycle, from the formation of the original massive stars to the incorporation of kilonova-produced elements into new planets, can span billions of years. Dr. Enrico Ramirez Ruiz, simulations have traced the long-term evolution of kilonova debris, describes the vast scales involved. We're talking about a recycling program that operates across the entire observable universe and over the entire history of cosmic time. Every atom of gold on Earth has been on a journey that likely began in a kilonova explosion billions of years ago. The cosmic recycling program also operates with remarkable chemical sophistication. Different types of stellar explosions produce different ratios of heavy elements, but kilonova explosions create R-process elements in ratios that remain remarkably consistent across different events. This consistency suggests that the R-process operates under universal physical conditions that don't vary significantly between different neutron star mergers. This consistency has profound implications for astrobiology. The heavy elements produced by kilonovae are essential for the complex chemistry that makes life possible. Molybdenum is crucial for certain enzymes. Iodine is essential for hormone production in many organisms, and rare earth elements play important roles in various biological processes. This consistency has profound implications for astrobiology. The heavy elements produced by kilonovae are essential for the complex chemistry that makes life possible. Without the cosmic recycling program operating through kilonova explosions, the chemical diversity necessary for complex life might never have developed. The recycling program also operates with perfect conservation. Nothing is truly lost in the cosmic economy. The neutron matter, locked away in neutron stars for billions of years, is eventually liberated and transformed into elements that can participate in chemistry, geology, and biology. Even the energy released during kilonova explosions isn't wasted. It helps to heat and stir the interstellar medium, contributing to the complex dynamics that govern galaxy evolution. As we'll explore next, this cosmic recycling program has had a direct and profound impact on our own planet and every living thing on it. The gold in our jewelry, the rare earth elements in our technology, even some of the elements in our bodies, all are products of the universe's most sophisticated recycling program, powered by the most violent explosions since the Big Bang. The wedding ring on your finger contains atoms that were forged in cosmic violence, so extreme it defies human comprehension. Every gram of gold on Earth carries within it the signature of ancient kilonova explosions, stellar collisions so catastrophic they briefly outshone entire galaxies. This isn't poetic metaphor, it's scientific fact. The connection between terrestrial gold and cosmic violence was suspected for decades, but GW170817 provided the first direct observational proof by measuring the amount of gold created in a single kilonova event and comparing it to the abundance of gold in our galaxy. Astronomers confirmed that neutron star mergers are indeed the primary source of Earth's most precious metals. The numbers are staggering. The kilonova from GW170817 alone produced approximately 10 Earth masses of gold. That's roughly 60 trillion tons of the precious metal, created in the span of just a few seconds. To put this in perspective, all the gold ever mined in human history amounts to less than 200,000 tons. The single kilonova explosion produced 300 billion times more gold than exists in all the jewelry, electronics, and central bank reserves on our planet combined. Dr. Edo Berger, whose team calculated the gold production from GW170817, explains the cosmic significance. We're not just talking about trace amounts of gold scattered through space. Kilonovae are industrial-scale element factories, producing quantities of heavy elements that boggle the mind. Every kilonova explosion represents a cosmic mining operation on a scale that dwarfs anything we could imagine. But gold is just the beginning. The same raw process that creates gold in kilonova explosions also produces platinum, silver, palladium, and dozens of other heavy elements that are crucial to modern technology and life itself. The platinum in catalytic converters, the silver in electrical contacts, the rare earth elements in smartphone displays, all trace their origins back to neutron star collisions that occurred billions of years ago. The path from kilonova explosion to Earth's crust is a journey that spans cosmic time. The heavy elements created in ancient neutron star mergers were dispersed through the interstellar medium, mixing with hydrogen and helium left over from the Big Bang. Over hundreds of millions of years, this enriched material gradually accumulated in the molecular cloud that would eventually collapse to form our solar system. When the solar nebula condensed 4.6 billion years ago, it contained the accumulated heavy element production of billions of years of stellar evolution and kilonova explosions. The gold, platinum, and other precious metals that sank to Earth's core during planetary formation carried with them the chemical fingerprints of these ancient cosmic catastrophes. Isotope analysis of Earth's oldest rocks reveals this kilonova heritage in remarkable detail. The ratios of different platinum group elements in terrestrial samples match the predicted outputs of R-process nucleosynthesis with extraordinary precision. It's as if each atom of precious metal contains a cosmic birth certificate, documenting its violent origin in a neutron star collision. The implications extend far beyond precious metals. Many of the trace elements essential for life itself were likely produced in kilonova explosions. Iodine, crucial for thyroid function, is an R-process element that probably originated in neutron star mergers. Molybdenum, essential for certain enzymes, follows the same cosmic pathway. Even some of the uranium that provides geothermal heat in Earth's interior was likely forged in the extreme conditions of kilonova explosions. Dr. Jennifer Johnson, whose research focuses on galactic chemical evolution, puts this in perspective. We tend to think of gold and other precious metals as rare and exotic, but from a cosmic perspective, they're simply the natural byproducts of stellar evolution. The fact that they're concentrated on planets like Earth is what makes them precious to us, but their creation is as fundamental to the universe as the formation of stars themselves. The kilonova legacy extends beyond individual elements to include the complex chemical processes that make advanced technology possible. Modern electronics depend on precise ratios of different rare earth elements, ratios that were established by the Rare process billions of years ago. The smartphone in your pocket contains dozens of elements that were created in kilonova explosions and refined by billions of years of cosmic chemical evolution. But perhaps most remarkably, the kilonova legacy includes the very possibility of complex chemistry itself. In a universe without neutron star mergers, the periodic table would end at iron. There would be no gold, no platinum, no uranium, none of the heavy elements that enable the rich chemistry of rocky planets and the complex biochemistry of life. The discovery that kilonovae are the primary source of our process elements has also revolutionized our understanding of planetary formation and habitability. Planets forming in regions of the galaxy with higher rates of neutron star mergers will have higher concentrations of heavy elements, potentially making them more geologically active and better able to maintain the chemical cycles necessary for life. Conversely, planets forming in the early universe, before kilonova explosions had time to enrich the interstellar medium with heavy elements, would be chemically simpler worlds, potentially less capable of supporting the complex chemistry that leads to life as we know it. The Goldmaker's legacy reaches into every aspect of our technological civilization and possibly our biological existence. Every electronic device, every piece of jewelry, every catalytic process that depends on precious metals carries within it the signature of cosmic violence so extreme it challenges our ability to comprehend it. We are, quite literally, children of the stars, and more specifically, children of the most violent stellar deaths in the universe. The influence of kilonova explosions extends far beyond creating heavy elements. These cosmic catastrophes fundamentally shape the evolution of galaxies themselves, acting as both creative forces and agents of destruction on scales that span millions of light-years and billions of years. Each kilonova explosion deposits enormous amounts of energy into the surrounding interstellar medium. The expanding shock waves heat gas to temperatures of millions of degrees, creating vast bubbles of hot plasma that can persist for millions of years. These superbubbles alter the structure and dynamics of entire galactic regions, influencing where and when new stars can form. The energy injection from kilonova explosions is so significant that it affects what astronomers call the baryon cycle, the ongoing exchange of matter between galaxies and the intergalactic medium. In smaller dwarf galaxies, a single powerful kilonova can actually blow gas completely out of the galaxy, stripping away the raw material needed for future star formation. Dr. Romel Davet, whose simulations model galaxy evolution over cosmic time, explains the large-scale impact. Kilonovae aren't just element factories. They're cosmic weather systems that can change the entire environment of a galaxy. Their energy output can suppress star formation for millions of years across regions hundreds of light-years in diameter. This galactic-scale influence creates complex feedback loops that regulate the pace of cosmic evolution. In the early universe, when galaxies were smaller and more fragile, kilonova explosions may have played a crucial role in determining which proto-galaxies survived to become the massive systems we observe today. Galaxies that experienced too many energetic explosions might have lost their gas and stopped forming stars, while those with more moderate kilonova rates could continue evolving. The chemical enrichment from kilonova explosions also drives what astronomers call galactic chemical evolution, the gradual increase in heavy element abundance over cosmic time. But this isn't a uniform process. Different regions of galaxies experience different rates of neutron star formation and merger, leading to chemical inhomogeneities that persist for billions of years. These chemical variations have profound implications for planetary system formation. Stars forming in regions that have been enriched by many ancient kilonova explosions will have higher concentrations of heavy elements, making them more likely to form rocky planets with complex chemistry. Conversely, stars forming in regions with fewer neutron star mergers will have lower heavy element abundances, potentially limiting their ability to form Earth-like worlds. The timing of kilonova explosions relative to galaxy formation also matters crucially. Early kilonova explosions, occurring when galaxies were still assembling, could disperse heavy elements across vast regions and even eject them into intergalactic space. Later explosions, occurring in more mature galaxies with deeper gravitational wells, are more likely to retain their heavy element production within the galaxy. Recent observations have revealed that the R-process element abundance in galaxies correlates with their star formation history in ways that reflect the unique properties of kilonova explosions. Unlike supernovae, which occur relatively soon after star formation, neutron star mergers can be delayed by billions of years, depending on the orbital evolution of the binary system. This delay creates what astronomers call delayed enrichment, a phenomenon where the heavy element abundance of a galaxy continues to increase long after its main episode of star formation has ended. Ancient elliptical galaxies, which formed most of their stars billions of years ago, are still experiencing kilonova explosions from binary neutron star systems that formed in their youth. The distribution of R-process elements within galaxies also provides crucial information about the physics of kilonova explosions themselves. By mapping how gold, europium, and other R-process elements are distributed across different galactic regions, astronomers can infer the typical velocities of kilonova ejecta and the efficiency of mixing with the interstellar medium. Dr. Chiaki Kobayashi, whose models trace chemical evolution across cosmic time, describes the complexity kilonovae create a kind of chemical archaeology in galaxies. By studying the current distribution of R-process elements, we can reconstruct the history of neutron star mergers going back billions of years. The role of kilonova explosions in galactic evolution is still being actively studied as astronomers develop more sophisticated models and better observational data. Future gravitational wave detections will provide direct measurements of kilonova rates in different types of galaxies, helping to refine our understanding of how these explosions influence cosmic evolution. The emerging picture is one of profound interconnection. Kilonova explosions don't occur in isolation, but are integral parts of the complex ecosystem that governs galaxy formation and evolution. These violent stellar deaths help determine which galaxies thrive, which fade away, and how the chemical complexity necessary for life spreads throughout the cosmos. The detection of GW 1708-17 marked not an ending, but a beginning. The launch of the most sophisticated cosmic surveillance network humanity has ever constructed. Today, a global array of gravitational wave detectors, electromagnetic telescopes, and rapid response systems stands ready to capture the next chapter in the story of cosmic violence. Hole 1 Sa. That Furiasao 7 marked a Neriasariasa marked a Lol. The advanced LIGO detectors in Louisiana and Washington have been joined by advanced Virgo in Italy, creating a 3-detector network that can pinpoint gravitational wave sources with unprecedented precision. When all 3 detectors operate simultaneously, they can localize binary neutron star mergers to regions of sky covering just a few square degrees, small enough for optical telescopes to search systematically for kilonova counterparts. But the network is expanding rapidly. CAGRA, a cryogenic gravitational wave detector built deep underground in the mountains of Japan, began operations in 2020. Its unique design, using sapphire mirrors cooled to just 20 degrees above absolute zero, promises to achieve sensitivities that surpass even the advanced LIGO detectors. India is constructing LIGO India, which will create a 5-detector global network capable of exquisite localization of gravitational wave sources. On 3D Central Record for idea, with detectors spread across 4 continents, this network will provide nearly continuous coverage of the sky, ensuring that kilonova explosions occurring anywhere in the observable universe have a good chance of being detected and followed up. Dr. Joe van den Brand, the spokesperson for the Virgo collaboration, describes the transformation. We've moved from the era of gravitational wave discovery to the era of gravitational wave astronomy. With multiple detectors operating simultaneously, we're not just detecting these cosmic collisions, we're studying them with the precision of laboratory experiments. The sensitivity improvements planned for the next generation of gravitational wave detectors are staggering. Advanced LIGO Plus will improve sensitivity by a factor of 2, effectively increasing the volume of space that can be searched for binary neutron star mergers by a factor of 8. This means that events like GW 170817, which was detected from a distance of 130 million light-years, will become detectable from distances of over 250 million light-years. But it's the proposed third-generation detectors that will truly revolutionize kilonova astronomy. The Einstein telescope, planned for construction in Europe, will be built underground in a triangular configuration with 10-kilometer arms. Its sensitivity will exceed current detectors by a factor of 10, making binary neutron star mergers detectable across the entire observable universe. Istok, Seer Vital Frozen, Sida Seer Arm. The Cosmic Explorer, planned for the United States, will push sensitivity even further with 40-kilometer arms, 10 times longer than current LIGO detectors. These instruments will be so sensitive that they'll detect every binary neutron star merger occurring anywhere in the observable universe, providing a complete census of kilonova explosions across cosmic time. The electromagnetic follow-up capabilities are evolving just as rapidly. The Large Synoptic Survey Telescope, now called the Vera C. Rubin Observatory, will begin operations in Chile, providing the ability to scan the entire visible sky every few nights with unprecedented depth and precision. When a gravitational wave alert is issued, Rubin Observatory will be able to identify kilonova counterparts within hours of the merger. Space-based observatories are also joining the hunt. The James Webb Space Telescope's infrared capabilities make it uniquely suited for studying the late-time evolution of kilonova explosions, when the emission shifts to infrared wavelengths dominated by heavy element decay. The Nancy Grace Roman Space Telescope will provide wide-field infrared imaging that could revolutionize our ability to find kilonova counterparts. The coordination between gravitational wave detectors and electromagnetic observatories has become increasingly sophisticated. Automated alert systems now notify thousands of astronomers within minutes of a gravitational wave detection, triggering coordinated follow-up campaigns that span the electromagnetic spectrum. Dr. Mansi Kasliwal, who pioneered many of the follow-up techniques used for GW 170817, explains the evolution. We've learned to work at the speed of the universe. When gravitational waves arrive on Earth, carrying news of a cosmic collision, we can now respond with telescopes around the world within minutes. It's like having a global emergency response system for cosmic violence. The improvements aren't limited to ground-based facilities. A new generation of gamma-ray satellites, including the Gravitational Wave Optical Transient Observer, GOTO, and the THESE-US mission, are being designed specifically to work in coordination with gravitational wave detectors. These missions will provide rapid, automated searches for the electromagnetic counterparts of neutron star mergers. Perhaps most excitingly, future gravitational wave detectors will be sensitive enough to provide early warning of approaching neutron star mergers. The most sensitive third-generation detectors will be able to detect binary neutron star systems hours or even days before they merge, providing astronomers with unprecedented opportunities to study the final phases of the cosmic death spiral. This early warning capability will transform kilonova astronomy from a reactive science to a predictive one. Instead of scrambling to identify optical counterparts after gravitational waves had been detected, astronomers will be able to position telescopes in advance, capturing the entire evolution of kilonova explosions from the moment of collision. The next decade promises to deliver dozens of kilonova detections, each providing new insights into neutron star physics, or process nucleosynthesis, and the violent processes that shape the cosmos. The hunt that began with GW 170817 is just getting started, and the most spectacular discoveries may still lie ahead. Beyond the current generation of gravitational wave detectors and electromagnetic observatories lies a future where humanity's ability to study cosmic violence will transcend every limitation that constrains us today. The next leap forward will come from space-based gravitational wave detectors, instruments so ambitious in scope that they will fundamentally change our relationship with the cosmos. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will consist of 3 spacecraft flying in formation 2.5 million kilometers apart, connected by laser beams that can detect gravitational waves with wavelengths millions of times longer than those accessible to ground-based detectors. LISA will be sensitive to gravitational waves from binary neutron star systems years or even decades before they merge. This extraordinary early warning capability will allow astronomers to study the final stages of binary evolution in unprecedented detail, watching as neutron stars spiral closer together over months or years of real-time observation. Dr. Carsten Dansman, whose team is developing the technology for LISA, describes the revolutionary potential. We'll go from detecting neutron star mergers when they happen to predicting exactly when and where they will happen. It's like the difference between studying lightning after it strikes and watching storm systems develop over days. But space-based detectors represent just one frontier in the hunt for kilonova explosions. The electromagnetic follow-up capabilities of the 2030s and beyond will dwarf anything available today. The Extremely Large Telescope, ELT, with its 39-meter mirror, will be able to obtain detailed spectra of kilonova explosions from distances so vast that we'll be studying events that occurred when the universe was a fraction of its current age. The Square Kilometer Array, SKA, when completed, will provide radio imaging capabilities thousands of times more powerful than current instruments. The long-term radio emission from kilonova explosions, the afterglow radiation produced as expanding debris interacts with the interstellar medium, will be traceable for decades after the initial explosion, providing unprecedented insights into how these events reshape their cosmic neighborhoods. Future space telescopes will push kilonova astronomy into entirely new regimes. The proposed Origin Space Telescope will provide infrared spectroscopy so sensitive that it can detect the cooling emission from kilonova debris clouds for years after the explosion, mapping the 3-dimensional distribution of newly created heavy elements as they expand into space. Even more ambitiously, proposed missions like the Large UV/Optical/IR Surveyor, ELVUVR, will provide imaging resolution comparable to the Hubble Space Telescope, but with mirrors up to 15 meters in diameter. These capabilities will allow astronomers to study kilonova explosions in nearby galaxies with the same detail that ground-based telescopes can achieve for events in our own cosmic neighborhood. The computational resources available for modeling kilonova explosions are also advancing exponentially. Exascale supercomputers, machines capable of performing a quintillion calculations per second, are beginning to come online, enabling simulations of neutron star mergers with unprecedented resolution and physical realism. Dr. Christian Ott, whose group develops computational models of stellar explosions, explains the significance. We're approaching the point where we can simulate every aspect of a kilonova explosion, from the quantum mechanical behavior of neutron star matter to the large-scale interaction with the galactic environment in a single comprehensive calculation. These advanced simulations will be crucial for interpreting the flood of observational data that next-generation instruments will provide. Understanding the complex 3-dimensional structure of kilonova explosions, the detailed nucleosynthesis processes that create heavy elements, and the long-term evolution of the expanding debris will require computational models that capture physics across dozens of orders of magnitude in space and time. Artificial intelligence and machine learning are also transforming how astronomers search for and analyze kilonova explosions. Automated systems can now scan millions of images for transient sources, identify potential kilonova candidates, and trigger follow-up observations faster than any human observer could manage. The combination of improved gravitational wave sensitivity, revolutionary electromagnetic capabilities, and advanced computational modeling promises to make the 2030s a golden age for kilonova astronomy. Instead of celebrating individual detections like GW170817, astronomers will be studying populations of hundreds or thousands of these events, mapping their properties across cosmic time, and using them to trace the chemical evolution of the entire universe. Instead of celebrating individual detections like GW1708170817, astronomers will be studying populations of hundreds or thousands of these events, mapping their properties across cosmic time, and using them to trace the chemical evolution of the entire universe. The hunt that began with a single extraordinary detection is evolving into a comprehensive survey of cosmic violence, and the most dramatic discoveries are likely still to come. Despite the revolutionary insights from GW170817 and subsequent kilonova discoveries, fundamental mysteries about these cosmic explosions remain unsolved, puzzles that challenge our understanding of physics under the most extreme conditions in the universe. Perhaps the most pressing question concerns the equation of state of neutron star matter, the relationship between pressure and density in material compressed beyond nuclear densities. Neutron stars represent the most extreme form of matter that can exist without collapsing into a black hole. Yet we still don't fully understand how this ultra-dense matter behaves under the crushing pressures found in neutron star cores. The collision of two neutron stars provides a unique laboratory for probing this exotic matter. The gravitational wave signal from the merger carries information about how easily the neutron stars can be deformed by tidal forces, a property that depends directly on the equation of state. But extracting this information requires gravitational wave detectors much more sensitive than current instruments. Dr. Tanja Hindera, whose research focuses on extracting neutron star properties from gravitational wave signals, explains the challenge. We need to measure incredibly subtle features in the gravitational wave signal, distortions that tell us how the neutron star's shapes change as they spiral together. It's like trying to determine the internal structure of an egg by listening to the sound it makes when you drop it. Future gravitational wave detectors will be sensitive enough to measure these tidal deformations with high precision, potentially resolving decades-old debates about the nature of matter at nuclear densities. Whole-do neutron star cores contain exotic particles like hyperons or kaons. Are there phase transitions to quark matter in the deepest regions? The answers lie hidden in the gravitational wave signals from neutron star mergers. Another major mystery concerns the diversity of kilonova explosions. GW170817 provided our first detailed look at a kilonova, but it may not be representative of the full population. Different neutron star masses, different binary mass ratios, and different orbital characteristics could all produce kilonova explosions with dramatically different properties. Some theoretical models predict that certain neutron star mergers might produce bright kilonovae that are tens of times more luminous than GW170817, while others might create faint kilonovae that would be barely detectable with current instruments. So too, the relative frequency of these different types of explosions has profound implications for understanding our process nucleosynthesis and heavy element production throughout cosmic history. The long-term fate of kilonova remnants also remains largely mysterious. We know that GW170817 likely produced a black hole within seconds of the merger, but the detailed process of black hole formation and the properties of the resulting object are still poorly understood. Does the black hole form through prompt collapse of the hypermassive neutron star, or does it result from gradual accretion of material over longer timescales? The answer matters for understanding what happens to the enormous magnetic fields and rapid rotation that characterize the merger remnant. Some models suggest that the formation of a highly magnetized, rapidly rotating black hole could power additional electromagnetic emission, perhaps explaining some of the unusual features observed in the long-term evolution of GW 170817. One of the most intriguing unsolved mysteries concerns the role of magnetic fields in kilonova explosions. Neutron stars have the strongest magnetic fields in the known universe, and when two such objects collide, the interaction of their magnetic fields could have dramatic effects on the explosion dynamics and the resulting electromagnetic emission. Dr. Riccardo Ciolfi, whose simulations include the effects of magnetic fields in neutron star mergers, describes the complexity. Magnetic fields add another layer of physics that we're only beginning to understand. They can affect how material is ejected from the merger, how jets are launched, and how the kilonova emission evolves over time. But including realistic magnetic field effects in our simulations pushes computational requirements to their absolute limits. The connection between kilonovae and other high-energy astrophysical phenomena also remains poorly understood. Are all short gamma-ray bursts produced by neutron star mergers, or are there other mechanisms that can create similar explosions? How do kilonova explosions compare to other types of stellar explosions in terms of their impact on galactic chemical evolution? Perhaps most fundamentally, we still don't have a complete picture of how often neutron star mergers occur throughout the universe. The detection rate from current gravitational wave observatories suggests that these events happen roughly once every 100,000 years in a galaxy like the Milky Way, but this estimate has large uncertainties and may not account for the full diversity of binary neutron star systems. Future observations will also need to address the metallicity problem. The question of how kilonova rates and properties depend on the heavy element content of their host galaxies. In the early universe, when heavy elements were scarce, binary neutron star systems might have formed with different properties than those we observe today. Understanding this evolution is crucial for using kilonova observations to trace cosmic chemical evolution back to the first billion years after the Big Bang. These unsolved mysteries represent more than just academic puzzles. They're key to understanding some of the most fundamental processes in the universe. The answers will come from the next generation of gravitational wave detectors, electromagnetic observatories, and theoretical models, building on the foundation laid by GW 170817 to reveal the full story of cosmic violence and creation. In the grand theater of the cosmos, the most profound paradox may be that the universe's greatest acts of destruction are simultaneously its most profound acts of creation. The collision of two neutron stars, an event so violent it shakes the very fabric of space-time, is also the process that forges the gold in our jewelry and the elements essential for life itself. This paradox challenges our earthbound intuitions about violence and creation. In our daily experience, destruction and creation seem like opposite forces. We build carefully and slowly. We destroy quickly and carelessly. But the universe operates by different rules, where the most catastrophic events are also the most creative, and where death and birth are not opposites, but different aspects of the same cosmic cycle. The violence of a kilonova explosion is almost incomprehensible. In the final milliseconds before collision, two neutron stars, objects so dense that atomic nuclei are crushed out of existence, hurtle toward each other at 30% the speed of light. The kinetic energy involved exceeds the rest mass energy of our entire solar system. When they collide, they create temperatures and pressures that haven't existed in the universe since the first moments after the Big Bang. Yet from this ultimate destruction emerges the raw material for future worlds. The collision doesn't simply destroy two neutron stars. It transforms them into something entirely new. The neutrons that were locked away in ultra-dense stellar cores for millions of years are suddenly liberated and recombined into the heaviest elements in the periodic table: gold, platinum, uranium, and dozens of other elements that are impossible to create in any other way emerge from the cosmic violence like phoenixes rising from ashes. Dr. Brian Schmidt, the Nobel Prize-winning astronomer whose work revealed the accelerating expansion of the universe, reflects on this cosmic irony. The universe seems almost designed to create through destruction. Every element heavier than iron in your body was forged in conditions so violent that they would instantly vaporize our entire planet. Yet without that violence, neither planets nor life could exist. This creative destruction operates on every scale in the cosmos. Stars forge lighter elements through the violence of nuclear fusion, burning hydrogen into helium at temperatures of millions of degrees. When massive stars die, they do so in supernova explosions that can outshine entire galaxies. Yet these same explosions scatter the elements necessary for rocky planets and life throughout space. But kilonovae represent the extreme end of this spectrum, the most violent events in the modern universe, and simultaneously the most creative. The ore-process nucleosynthesis that occurs during neutron star mergers is so efficient at creating heavy elements that a single event can produce more gold than our sun will create in its entire 10 billion year lifetime. The philosophical implications are staggering. If we trace the history of any heavy element, the silver in our electronics, the gold in our art, the rare earth elements in our technology, we find that it was born in a moment of cosmic violence, so extreme that it briefly warped space-time itself. The most precious and beautiful objects of human civilization carry within their atomic structure the signature of destruction beyond imagination. This cosmic perspective forces us to reconsider our understanding of both violence and creation. In human affairs, we typically view these as moral opposites, violence as inherently destructive, creation as inherently good. But the universe recognizes no such distinction. The same physical processes that create also destroy, and the same forces that destroy also create. The collision that destroyed two neutron stars in a galaxy 130 million light-years away simultaneously created the elements that make possible the complex chemistry of life, the geological processes that keep planets habitable, and the technological civilization that allowed us to detect the collision in the first place. Without that ancient violence, we would not exist to contemplate its meaning. This paradox extends beyond element creation to the very structure of the cosmos. The Big Bang itself was the ultimate act of creative destruction, an explosion that destroyed the primordial singularity, while simultaneously creating space, time, matter, and energy. Every subsequent act of cosmic violence, from stellar explosions to galactic collisions, has continued this pattern of destruction, enabling creation. The universe's creative violence also operates across time, in ways that challenge human intuition. The heavy elements created in kilonova explosions billions of years ago are still creating new possibilities today. Every smartphone, every piece of modern technology, every complex molecule in our bodies represents the ongoing creative legacy of ancient cosmic destruction. Perhaps most remarkably, the violence that creates heavy elements also creates the conditions necessary for life to contemplate its own origins. The radioactive decay of elements produced in ancient kilonova explosions provides much of the heat that drives geological processes on Earth. Plate tectonics, volcanic activity, and the magnetic field that protects us from cosmic radiation all depend on the energy released by elements forged in neutron star collisions billions of years ago. In this cosmic perspective, violence and creation reveal themselves not as opposites, but as complementary aspects of a single process, the universe's ongoing transformation of simple into complex, uniform into diverse, and potential into reality. The most violent events since the Big Bang are also the most creative, and it is through embracing this paradox that we begin to understand our true place in the cosmic order. Look at your hands. In the atoms that compose your flesh lies a story that spans the entire history of the universe, a tale of cosmic violence, stellar death, and the gradual assembly of complexity from primordial simplicity. The hydrogen in your body is as old as the universe itself, forged in the first minutes after the Big Bang, when protons and electrons combined for the first time. But every other element in your body, the carbon in your DNA, the oxygen you breathe, the iron in your blood, was created inside stars or during their violent deaths. Your body is quite literally made of star stuff, but the story is more specific and more remarkable than Carl Sagan's famous phrase suggests. The different elements in your body were created by different stellar processes, at different times, in different types of cosmic violence. You are not just made of star stuff, you are made of the remnants of stellar catastrophes, spanning billions of years of cosmic evolution. The carbon atoms in your DNA were forged in the nuclear furnaces of stars through the triple alpha process, a delicate nuclear reaction that requires precise conditions to convert helium into carbon. The oxygen you breathe was created when massive stars burned carbon and helium in their cores, building up heavier elements layer by layer until their nuclear fuel was exhausted. But the trace elements that make life possible tell a different story, a story of the most violent events in the cosmos. The iron in your hemoglobin was created during supernova explosions, when massive stars underwent core collapse and rebounded in explosions that briefly outshone entire galaxies. The calcium in your bones, the sulfur in your proteins, the phosphorus in your ATP, all were forged in the nuclear cauldrons of dying stars. And then there are the elements whose origins trace directly back to events like GW 170817. The iodine in your thyroid gland was almost certainly created during a kilonova explosion, the collision of two neutron stars that occurred billions of years ago in some distant corner of the universe. The same is true for many of the trace elements that enable crucial biological processes, molybdenum in certain enzymes, selenium in antioxidant systems, even tiny amounts of rare earth elements that some organisms have learned to incorporate into specialized biological functions. Dr. Anna Friebel, whose research focuses on the oldest stars in our galaxy, puts this in perspective. When we study ancient stars that formed just a few 100 million years after the Big Bang, we see the fingerprints of the first kilonova explosions in their chemical composition. Those same elements are now part of our own bodies. We are directly connected to the universe's first moments of cosmic violence. The path from kilonova explosion to human biology is a journey that spans cosmic time and space. Heavy elements created in neutron star collisions were dispersed through the interstellar medium by expanding shock waves traveling at thousands of kilometers per second. Over millions of years, these elements mixed with hydrogen and helium to form molecular clouds that eventually collapsed to form new generations of stars and planets. Our solar system formed 4.6 billion years ago from material that had been enriched by billions of years of stellar evolution and cosmic explosions. The heavy elements that sank to Earth's core during planetary formation, the elements that became incorporated into the first organic molecules, the elements that now flow through your bloodstream, all carry the chemical signatures of their violent cosmic origins. But the connection goes deeper than just elemental composition. Many of the fundamental processes that make life possible depend on the specific properties of heavy elements created in kilonova explosions. The complex chemistry of DNA repair mechanisms relies on trace metals forged in neutron star collisions. The electron transport chains that power cellular respiration depend on iron-sulfur clusters that contain atoms created in stellar explosions billions of years ago. Even the energy that powers life on Earth has cosmic origins. While sunlight drives photosynthesis and most biological processes, the geothermal energy that keeps our planet's interior hot and geologically active comes largely from the radioactive decay of elements like uranium and thorium, elements that were created in kilonova explosions and incorporated into Earth during its formation. This elemental heritage connects every living thing on Earth to the most violent events in cosmic history. The atoms in your body have traveled through space for billions of years, survived the formation of the solar system, and been recycled through countless generations of life before becoming part of you. You are not separate from the universe. You are a conscious collection of atoms that the universe has temporarily organized into a pattern capable of contemplating its own origins. Your very existence is proof that the universe's greatest acts of destruction are also its most profound acts of creation. As we peer into the cosmic future, one truth becomes inescapably clear: the universe's age of violence is far from over. The neutron star collisions we observe today are merely the latest chapter in a story of cosmic destruction and creation that will continue for trillions upon trillions of years to come. The binary neutron star systems forming today will produce kilonova explosions billions of years in the future, when our sun has exhausted its fuel and Earth has become a frozen, lifeless world. The heavy elements created in these future collisions will enrich galaxies that have not yet formed, providing the raw materials for stellar systems and potentially life forms that we cannot even imagine. But the story of cosmic violence extends far beyond neutron star mergers. As the universe ages and expands, stellar evolution will produce increasingly exotic forms of destruction and creation. In the far future, when ordinary hydrogen-burning stars have become rare, the cosmos will be dominated by white dwarf stars, the slowly cooling remnants of stars like our sun. These white dwarfs will occasionally collide or accrete material from companions, creating Type Ia supernovae that may become the dominant form of cosmic violence in the universe's middle age. Unlike core collapse supernovae, which require massive stars that burn out quickly, Type Ia supernovae can occur billions of years after star formation has essentially ceased, continuing to create and distribute heavy elements long after the era of kilonova explosions has ended. Dr. Dan Maus, whose research focuses on the long-term evolution of stellar populations, explains the cosmic timeline. We're living in the universe's age of abundance, when massive stars are still forming and neutron star mergers are still occurring regularly. But this is a brief epoch in cosmic history. The real story of the universe will play out over timescales that make the current age of the cosmos seem like a fleeting moment. Even more exotic forms of cosmic violence may await in the distant future. As galaxies continue to merge and grow, some will develop supermassive black holes with masses billions of times that of our sun. When two such galaxies collide, their central black holes will eventually merge in events that produce gravitational waves far more powerful than any neutron star collision. These supermassive black hole mergers will create gravitational wave signals so strong that they could be detected across the entire observable universe by future space-based detectors. The collisions will also trigger massive outflows of gas and energy that could reshape entire galactic clusters, creating new episodes of star formation and heavy element synthesis on scales that dwarf individual stellar explosions. But perhaps the most profound form of future cosmic violence will be the gradual death of stars themselves. As the universe continues to expand and cool, star formation will gradually decline, as the available gas is either consumed or dispersed beyond the gravitational reach of galaxies. The last generation of stars will burn out in a cosmos that has become cold and dark, their deaths marking the end of the universe's age of nuclear fusion. Yet even in this seemingly sterile future, violence and creation will continue. Proton decay, if it occurs as some theories predict, will represent the ultimate form of cosmic destruction, gradually dismantling every atom in the universe over timescales of 10 circumflex 36 years or more. This process would release energy that could power entirely new forms of cosmic evolution, perhaps creating exotic forms of matter and energy that bear no resemblance to anything in the universe today. The far future may also bring forms of violence that we can barely imagine. Quantum fluctuations in the vacuum of space could occasionally create false vacuum decay. Events, cosmic phase transitions that propagate at the speed of light and fundamentally alter the laws of physics in their wake. Such events would represent the ultimate form of creative destruction, potentially giving birth to entirely new forms of matter and energy governed by different physical laws. Dr. Katie Fries, whose research explores the universe's ultimate fate, describes these possibilities. We tend to think of the current universe as permanent and stable, but it may represent just one phase in an eternal cycle of destruction and creation. The violence we observe today, kilonova explosions, stellar deaths, galactic collisions, may be just the prelude to forms of cosmic transformation that we can't even conceive. The implications for intelligence and consciousness in such a universe are staggering. If life and intelligence can adapt and evolve over these cosmic timescales, future forms of consciousness might witness and perhaps even participate in forms of cosmic violence that make kilonova explosions seem gentle by comparison. Advanced civilizations might learn to harness the energy of stellar collisions, black hole mergers, or even proton decay to power forms of existence that transcend our current understanding. But perhaps the most remarkable aspect of the universe's future violence is that it will continue the same fundamental pattern we observe today: destruction enabling creation, chaos giving birth to order, and violence serving as the engine of cosmic evolution. The heavy elements created in kilonova explosions today will be recycled through countless future generations of stars and planets, possibly enabling forms of chemistry and life that we cannot imagine. The universe's story is ultimately one of transformation, the gradual conversion of simple into complex, uniform into diverse, and potential into reality. This transformation requires violence, destruction, and death, but it also creates beauty and complexity and the possibility of consciousness capable of contemplating its own origins. As we look to the future, we can be certain that the cosmos will continue to surprise us with new forms of violence and new types of creation. The kilonova explosion we witnessed in GW 170817 was just one note in a cosmic symphony that has been playing for 13.8 billion years and will continue for trillions of years to come. In this vast temporal perspective, our brief moment of consciousness becomes both infinitesimally small and profoundly significant. We exist during the universe's age of greatest violence and creativity, at the cosmic moment when neutron stars collide and scatter gold across space, when massive stars explode and seed the cosmos with the elements of life. We are the universe's way of experiencing its own violence and recognizing its own creativity. In studying kilonova explosions, we are not just learning about cosmic physics, we are participating in the universe's ongoing process of self-discovery, using consciousness that arose from ancient stellar violence to understand the violence that continues to shape our cosmic home. We have journeyed into the heart of cosmic violence and discovered a profound truth. The most destructive events since the Big Bang are simultaneously the most creative. Every atom of gold ever forged, every element heavier than iron in your body, all born in violence beyond imagination. GW 170817 was more than a scientific discovery. It was proof that we live in a universe where death enables life, where stellar corpses become cosmic creators, where the most extreme physics gives birth to the chemistry that makes consciousness possible. The kilonova that blazed 130 million light-years away has faded to darkness, but its legacy lives on in every smartphone, every piece of jewelry, every complex molecule that enables thought itself. We are not separate from this cosmic violence. We are its children, made from atoms forged in collisions that shook space-time itself, conscious stardust contemplating the very processes that created us. The universe continues its ancient dance of destruction and creation. More neutron stars spiral toward collision. More kilonovae will light the cosmic darkness. More heavy elements will scatter across space, seeding future worlds we will never see. In the end, we are both witnesses to cosmic violence and living proof of its creative power. What strikes you most about this cosmic connection between violence and creation? Are you amazed that your body contains atoms forged in stellar explosions? Or does the vast timescale of cosmic evolution leave you feeling small? Share your thoughts in the comments below. If this journey through cosmic violence has sparked your curiosity about the universe's most extreme events, I'm grateful to have shared it with you. Consider subscribing to join me as we continue exploring the cosmos. 2. There are countless more stories of cosmic drama waiting to be told. The universe has many more secrets to reveal. If you're ready to dive deeper into the cosmic mysteries that surround us, explore our complete collection of space documentaries. Each one offers another piece of the grand puzzle of cosmic evolution, another chapter in the ongoing story of how violence and creation shape our extraordinary universe.